Okay, hello everyone, and welcome back to the stream. It's been a while. Good to see you again. It looks like my audio is okay, but just in case, as usual, let me know in the chat if you can or can't hear me. I would appreciate that. And also, as usual, let me know where you're watching from. We always have a very international audience. It's good to know where you guys are watching from. And if you're wondering, I am here in Japan. Sounds good? Okay. Thanks, Aaron. Thanks, everyone. Watching from Los Angeles. Nice. From Algeria. Welcome. Welcome, Nidal. Green Bay, Iraq, India, Somalia, Brazil. Awesome. All right, Peru, more India. Good. Okay, so again, welcome to the stream. Today's stream is going to be about DMVPN. Now, that is a very important topic in the CCNP. I did mention it in the CCNA course. So if you're studying my CCNA course and you've gotten to, I believe, day 53, let me confirm that. I think it's day 53 of the course, where I talk about WAN architectures, and I do briefly mention DMVPN. Let me just confirm. Yeah, day 53. So if you're on my CCNA course and you've reached day 53, I do briefly mention DMVPN. It's a VPN technology that Cisco developed. I won't get into it in any depth here because we're going to do a very deep dive here with Kelvin in a minute. But it's definitely something you should know at the CCNP level and beyond, especially for the NRC specialization. It's a very big topic. Okay, yeah, thanks guys. Thanks for confirming that. So I think we'll get our guest on. Kelvin, nod if you're okay. All good to go? All right, there we go. So let's bring on, once again, Kelvin.
Hi.
Hey, you're on. You're live. Welcome back.
Yeah, it's been a little while.
Yeah, it has. Is this our fourth stream? I think so. We did Juniper.
Something like that. Yeah, we did Junos, Multicast, MPLS. Yeah, fourth.
Okay, so yeah, so the fourth stream with Kelvin, fourth deep dive on a very important topic. Yep. I guess the Juniper one wasn't exactly a deep dive. That was more of a intro to Juniper, but MPLS and Multicast.
Well, Juniper's Juniper.
Yeah. Right. Okay, so what are you going to show us today?
So today, if I can share my screen real quick, we're going to be taking a look at is DMVPN. So I'm currently staying with Topology. I was telling Jeremy this story before I got on. The earbuds that I use to do the audio monitoring for the stream, the ear tip snapped in half this afternoon, so I had to make a very emergency run to Apple to buy some new headphones. Just got back a few moments ago, so I haven't had time to set up the Topology, and it's what I'm doing right now. So these nodes are rebooting here, and while they do that,
could you walk us through the topology then? Like sort of what's going on?
So what you'll notice here is if you've watched the multicast and MPLS videos, you'll notice this is a very simple topology. And part of the reason for that is simply that, I should probably close off my other applications here. Again, I haven't prepared for the stream at all. Part of the reason for that is because DMVPN is an overlay tunnel. So we're going to talk about what that means in more detail soon enough. But the requirement for DMVPN is basically that you have IP reachability between the nodes that you need to form tunnels between. So if you're labbing DMVPN, you don't need to focus on some elaborate transport. Obviously, no one's stopping you if you hate your time, but for the purposes of getting familiar with the DMVPN's intricacies there, a simple topology like this will work. In this case, this is literally just an unmanaged switch here, and we're going to put all these guys on the same subnet. Because again, what matters in this context is the overlay topology that we're using rather than having the most extravagant routing set up in our transport. Again, as long as you've got IP reachability between the various nodes here, you should be fine.
Yep. And I do explain the concepts of overlay and underlay in the CCNA course.
Get to that, as soon as my devices decide that they want to stop messing with me.
Hey, last time I tried to do a stream with CML, it just died on me, so you're doing better than I did.
Well. So while I fire up I'm gonna fire up a whiteboard here so that we can get crack-a-lackin'.
Nice. Good terminology. I like that vocabulary.
I know, right? Super technical. Happy April Fools, by the way. Hopefully no one got...
Anyone got fooled?
Got pranked too hard.
Yeah, it's already over. It's the second here in Japan.
I'm not spared from it just yet. It looks like Painter wants to pull an April Fool's prank on me. There we go. All right. We can speed this up here. I'd love it. There we go. Let's launch IP Evo real quick. And is this mapped to the correct monitor? No, it's not. Fun. Give me just a second
to
get this remapped.
No rush.
Actually, it will probably be simpler to do this. Let me stop my share real quick, and then I'll share from the other monitor, because that's where this is mapped to.
Yeah, sure.
So let's drag this over here. So let's go for a share again. Try 2, this time on the right monitor.
Yeah. And by the way, everyone in the chat, let me know if our audio is balanced well, like if he's too loud or if I'm too loud. It looks okay on my end, but I'm not really sure.
Is that true? Cool.
Yep.
Okay. So this stream is primarily going to be about DMVPN. If we get time at the end, I have a certificate authority where we might mess around with some FlexVPN, which is unofficially coined DMVPN Phase 4. But for the time being, we'll just focus the majority of this stream on DMVPN. So the topology that I've got here, I'll draw 2 topologies. First is the actual underlay topology. So we saw it in the CML there. The underlay topology is simple as eggs. We've just got the hub routers, so we've got 2 of them here. We've got spoke 1 here, and then spoke 3, 4, and 5. Yes, I know I didn't draw them in the best order. Sue me. So, point here is that these guys are all going to be on the same subnet. I'll put them on the 192.168.1.0 subnet, but it doesn't really matter. Again, what matters is that these guys can ping each other effectively. They have IP reachability, which in this case, because they're just all connected to a switch on the same VLAN, they're going to have IP reachability to each other within the subnet. So that requirement is all taken care of. This is the underlay topology, or in DMVPN documentation right here is referred to as the transport or the IP transport here.
Would you say that's basically like the physical network?
Right.
Like the physical topology?
So the actual meat and potatoes network that's actually running underneath.
Yep.
So your underlay would consist of your physical routers, physical switches, all of that, what constitutes the transport path.
Yeah.
And then...
Oh, we got one question. Aren't hubs normally connected to spokes? Yeah, why aren't all the spokes directly connected to the hub like this?
Well, again, the concept of the underlay here is mainly that we all have reachability to each other. Yep. When we actually do get the DMVPN configuration in a moment here, we are going to set up the spokes to register to the hub. But underlay-wise, again, the only requirement is that everyone that needs reachability to each other has reachability to each other.
Yep.
So
Yep.
If the hubs can reach the spokes, we're good. And when we start to do the spoke tunnels, if the spokes can reach the spokes, then we're good.
Yep.
So no, we don't have to have them directly connected in the transport as long as the transport can facilitate reachability between the hub and the spokes. We're good.
Yeah,
If they can't, then we have a separate problem.
Yeah.
But no, they don't have to be directly connected. Yeah. So moving on from the concepts of the underlay, we have the overlay. And I'm sure, Jeremy, you've covered this in your CCNA course, but just to rehash it here.
Yeah, feel free.
The idea is that the overlay is the path we're actually following, right? So this underlay transport here tells us a lot about how the network is built, but it doesn't tell us about how the data is actually flowing, right? So if we're building any overlay services here that run over the network, those can have essentially disconnected topologies. So in the overlay, when we're actually configuring a DMVPN, this, as one of your viewers pointed out, does follow the hub and spoke model, right? Where we've got hub 1 up here, hub 2 down here. We've got whatever cloud we're working with here, and then we've got the spokes.
Yeah, so the hub and spoke of DMVPN is in the overlay.
The overlay,
yeah.
Right.
That doesn't necessarily mean the underlay is a hub and spoke topology. Probably
and
isn't.
For the most part, DMVPN doesn't actually really care what your underlay is.
Yeah.
Again, just as long as you've got IP reachability, which is the point I'm going to keep stressing here. So the purpose for DMVPN is clearer if you think about what the DMVPN is looking to replace or looking to solve, right? What problem it's looking to alleviate. So one of the main problems with private WAN services is that they're expensive, right? Compared to a internet connection, at least. If you're looking at something like when DMVPN came out, it would have been things like frame relay or MPLS or whatever case may be. However you're getting your private WAN connection to do site interconnections there, the problem is that they're expensive, right? Yeah. And a lot of the times, the cost can't easily be justified, right? So for things like voice, where you need assurance, that's where you can start justifying the cost of a costly private WAN connection, where you need that assurance, where you need to handle things like MPLS, QoS, where you need assurance that the service provider is going to meet some minimum SLA. But the internet doesn't have that sort of assurance, but you don't always need it, right? If you're just trying to, for example, run a TCP stream, or you're trying to get to a web server that's hosted on your headquarters, you don't need the best connection. You don't absolutely need assurance. So for that purpose, the internet works just fine. But then you have the problem of, well, how do you interconnect your sites over the internet, right? That becomes a significant challenge, because you have to think about things like NAT. You have to think about how the traffic flow is actually going to work, whether it's going to be punted straight to the hub every time, or whether you can do spoke to spoke. There's a lot of considerations there when you're actually trying to build your VPNs over the internet. Now, you're familiar with things like SD-WAN. SD-WAN is the more modern solution for handling site-to-site VPNs over the internet, where it's basically an automated fabric there. But before SD-WAN, we had a couple of technologies, one of which is DMVPN. FlexVPN came out. FlexVPN is Cisco's push to implement unified IPsec workflow. We'll talk about that later. And then one of the intermediaries between DMVPN and SD-WAN there was IWAN, which is Cisco's intelligent WAN service that integrated with their APIC EM controller for their SDN. We won't talk about IWAN here because it's mostly not relevant. No certification covers it. But we will talk about its predecessor, which is DMVPN. So getting back to the topology here, in the overlay, we've got these point-to-multipoint tunnels, and that's really the bread and butter of DMVPN here. It's building these point-to-multipoint tunnels because the alternative is that on your hub routers here, you're building individual, I want it pink there, you're building individual site-to-site tunnels.
Yep.
So before DMVPN, this was your option. It was basically build 5 GRE tunnels here, going over the internet, which is a pain in the butt because now you have to scale your tunnel interface count by the number of spokes you've got, which is bad from a manageability perspective, and it adds a lot of strain to that router for a lot of reasons there. Now, the way the DMVPN ends up working is it's a point-to-multipoint tunnel, meaning that we've got one point here on the hub, and this is terminating multiple tunnels effectively out to the spokes.
Yeah, and I have a question relevant to that there, or from the chat. It says, sorry, what do you mean by hub router? I think he might be confusing hub with an Ethernet hub. What does hub mean in this context?
So hub in this context is referring to the hub and spoke logical topology here.
Yep.
So what this effectively means, and let me create a new layer here, this might help. So I'm not crowding this layer up with that. If we're looking at isolating this topology here into, let's say, one hub and one spoke, the spoke routers connect to the hub. That's the goal of the hub and spoke topology here. It's that we have this hub router that's aggregating connections to our spokes here. So let's say spoke 1 wants to talk to spoke 2. In this simplified topology, it would go through the hub, down the spokes. If you think about something like the spine leaf topology, you can make sort of a parallel there. Obviously, there's going to be some differences, but you can think about your spines as your hubs and then your leaves as your spokes there. So if you're familiar with the concepts of spine and leaf there, you can make a parallel between that and hub and spoke because there are parallels to be made there. But your hub router is just there to service the next layer up from your spoke or your spoke routers there.
Yep.
Hopefully that clarifies that.
Yeah. So you'll see in the logical topology, all of the spoke routers, they all connect to that central hub router.
Yeah. And the term here is registration. So we'll talk about how NHRP works soon. These spoke routers are all going to register up to the hub, and in the DMVPN world, the hub is the glue that puts this entire solution together. So that's the use case there for DMVPN. It's simplifying the configuration of overlay VPN tunnels there between your sites. So moving on to the technology breakdown then, because DMVPN is really a misnomer, right? We've got one DMVPN command on iOS, and that's show DMVPN. But you'll never go into an interface and say DMVPN, blah, 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 right? DMVPN is the name of the overall solution. The solution has 3 components. We've got GRE, which is going to be our data plane encapsulation. And I'll talk about how we're actually using GRE, because we're using a special flavor of it. You can call it that, called mGRE. Then we're looking at NHRP. I'm using a different blue, but whatever. NHRP is going to be the control plane protocol that glues all this together. I'll elaborate more on NHRP because there's a lot to be talked about in that regard. And then finally, so these are the 2 sort of required elements here. So you need GRE because you don't have a tunnel if you don't have a data plane. And you need NHRP because that's actually going to allow you to do your next hop resolution over the tunnel. The optional component here is going to be IPsec. So you can apply IPsec encryption, particularly if you're running your VPN over things like the internet, where we call it the Wild West. There's very little assurances there. So if you're running your VPN over things like the internet, you might be very hesitant to run sensitive organizational data over your internet VPN there if you don't have it encrypted. So that's what IPsec is going to help us do. But this isn't required. Your DMVPN will function just fine without IPsec. It's just that part of the logic here is going to be, if you are going through the work of configuring a DMVPN, applying an IPsec profile is just one more command on the tunnel. And creating your IPsec parameters isn't all that difficult either. So if you're putting in the work to design a DMVPN, the logic here, the argument is that in most cases, you should just put in the extra work of implementing IPsec anyway. In that context, the benefits would outweigh the costs. But it is worthwhile to know that this isn't technically a required element. It's an optional element, and your DMVPN is going to come up just fine without it. It just obviously won't be encrypted. It'll be in plain. Everything is going to be sent at the network and transport layer, at least in plain text. Your application, obviously, like HTTPS, could do TLS encryption or whatever the case may be there. So covering GRE first. GRE, and if you guys have dealt with simple point-to-point GRE tunnels, you'll be very familiar with this concept. GRE is a tunnel encapsulation that we can use to essentially, tunnel data over our networks here. So this is how we typically visualize these tunnels in our topology diagrams. And we're running GRE here, which I'll show in packet captures later, is just an encapsulation. So GRE is encapsulating the original IP packet as it gets routed through this tunnel, which is a logical interface on the router. It's encapsulating the traffic as it gets put through this tunnel. And then effectively, we've got the original packet. We've got the GRE header being put on the outside here. And then we have another packet. So we've got the outer packet is what it's called. So the devices in the underlay or in the actual transport path are going to be routing based on this outer packet here. And this GRE is effectively masking the original packet on the inside there. So it's effectively hiding it from these devices in the underlay, which is why we call it tunneling. We're creating a tunnel between our endpoints here, and then we're pushing this traffic through the tunnel using GRE to, again, mask the traffic from the underlay devices. So again, the underlay devices, when you're using GRE, they're routing using this outer IP header, which contains the underlay IP addresses. This original IP header contains the source and destination IP addresses in the overlay. So let's erase that real quick. So that's standard point-to-point GRE. Now, again, if you've configured GRE, you'll know that when you're doing GRE, two of the parameters you have to set are the source and the destination, right?
Yep.
So you have to, and that impacts what you use on the outer header, right? So your source is going to be the source IP address of the outer header that I just showed, and your tunnel destination is going to be the destination IP address of the outer IP header that I just showed. The problem when you get into DMVPN is we mentioned it was a point-to-multipoint tunnel. So we have a clear source. This is our source, right? This right here. Oh, right. I need to select the active layer. Here we go. Okay. So this is going to be our source here, right? We have a very clear source, let's say on hub 1, but what's our destination, right? Well, you would say, okay, well, it's all 5 of these guys, right? Except, the problem here is we have to set one destination, and there's no way to set one particular destination here. It doesn't even make sense to say that, right? The destination of this tunnel isn't one thing. It's all 5 of these spokes and however many spokes we add on, and whatever other devices are in our DMVPN topology. So it doesn't make sense, again, to say, here's a tunnel destination, because we can't. So this is where mGRE comes into play. And mGRE stands for multi-point GRE. So with multi-point GRE, all we have to do is specify the source. We don't have to specify the destination for the tunnel to come up. But then now you have to bring in the question of, okay, well, the tunnel is going to come up, but how do we know what the destination IP address in the outer header is going to be? Well, that's where NHRP comes in, right? So with multi-point GRE, again, we specified the source. We didn't specify a destination. The way that the devices know what destination IP address to use in the outer IP header to get the traffic forwarded to whatever device in the DMVPN fabric has to go to is using the next hop resolution protocol. And the way it works, and we'll again look at this in much greater detail when we actually look at topology, is something like this. So when the spokes come on in fabric, and here's where the hub becomes relevant, because in the context of an NHRP, this is where our hubs do their heavy lifting. The spokes, when they come up on the fabric, are going to register themselves using an NHRP to the hub. And part of this registration message, there's a lot of information in there, but part of this registration message is going to contain the overlay IP address, so a tunnel IP address, and then the underlay, or what we call the NBMA address. And so I forgot to add this term here, NBMA, non-broadcast multi-access. So NBMA, underlay, in this context, it's all the same thing. So the NBMA, or the underlay IP address, and the overlay IP all get advertised in the registration to the hub, and then all these folks are going to do the same thing. So at this point, the hub has a database of all of the spokes, their tunnel IP addresses, and then the mapping between that and the NBMA IP address, which is what we need in order to substitute for the tunnel destination mGRE configuration there. So effectively, when these devices want to send traffic to each other, what they're going to do is they're going to do a resolution. That's what the R comes in NHRP. They're going to send a resolution request to the hub, and then the hub is going to respond back with that mapping there. And we'll see this concept start to evolve when we get to actually implementing this. So that's the bulk of the introductory theory that you need to understand in order to know what the heck I'm doing on the CLI. It's knowing that DMVPN uses a tunnel interface. It's an overlay tunnel. It uses mGRE and NHRP as its two primary key components to work. And then the other concepts I've mentioned here as to how mGRE and NHRP specifically contribute to the DMVPN fabric. This is a very theory-heavy concept there, but once you get to implementing the CLI, as it was with MPLS, as it was with multicast, a lot of these concepts are going to start to become much clearer than just whiteboarding it. So speaking of which, before I move on to whiteboarding it, are there any questions I need to address? Or not labbing it, sorry, my bad.
Yeah, not really at the moment. I'm sure more will come up, but seems real good.
Cool. This is coffee, by the way. So let me go ahead and actually, no, I'll just use this monitor. That's fine. So what I did before what I had to do before the stream there was, let's see, hold on. What I had to do for the stream there was these are the new Cat 8K routers. I don't know if they'll actually show them in the show version. It won't. The Cat 8K is the successor to the CSR 1000V. So I have to, or I'm using the virtual Cat 8Ks here. And the problem here is that the licensing is much more restrictive than it was with the CSR because it's using a new licensing model. So basically what that means is in order to get the IPsec working, I had to do license, boot level, and change this from Essentials to, I changed it to Premiere because there's really no reason why not, and then add on DNA Premiere. After you do is it'll prompt me to reload, so reload, and you're good. So if you're working with the new Cat 8Ks, which is included in the newest CML release, the newest release of the reference platform there, and you're working with C8Ks and you're wondering, I think I should be able to show this because this is a C8K, I think. Yeah, and I didn't reset the licensing. So if you show crypto here, you're not going to see the IPsec components that you're going to need to do FlexVPN or just IPsec encrypted DMVPN there. So in that case, you reset the license, reload, and you'll get all of your fancy crypto commands back for configuring your IPsec there. So just a little oddity there. I was joking with Jeremy before the stream. They'll let you configure all the PKI you want, but don't you dare talk about IPsec. So. what we're going to do here, besides the licensing, I didn't have time to do much configuration. So I'm going to paste in some boilerplate config, gigabit 1, and we're going to no shut this. Now, again, the the underlay topology here is going to be very simple. We're putting all this on one subnet, and then in the overlay, that's where we're going to start doing our differentiation. So overlay here, underlay, I'm just gonna give it IP address of 0.11 here, and that should be that. And then so here's the underlay configuration. Did I no shut this? Yeah, I did. Cool. And I should probably paste that boilerplate config in here. There we go. I'll add this in boilerplate config. Makes it easier. And just to prove the point that all you need is IP reachability, what I'm going to do is something a little interesting here. I'm going to create loopbacks on these routers here, and then advertise them through the underlay using a routing protocol. That's going to give me the context I need to implement a feature to optimize the DMVPN later called an VRF. So let's give this guy its last IP. And what I'm going to do here is the CA is going to need its own IP, so I'll just give it 100. And if we get time to do flex VPN, that's where the CA is going to come into play. So what I'm going to end up doing here is I'm going to create a loopback interface, and then I'm going to say 10.255.255.11. So I'm going to assign this a loopback address here. And this is going to be our underlay address. And again, I'm just doing this to prove the point that all you need is IP reachability underlay. So it doesn't even matter what addresses you're using, again, as long as you've got reachability in the underlay. And that is a point I cannot stress enough. So what I'm going to do, I'm going to do OSPF, and solely because I can do OSPF from the interface. that's my only reason for choosing OSPF in this context.
That's good enough reason as any.
Yeah. So let's skip over the internet node. The internet node is just a relic from when I had the internet as the hub. Then I figured I didn't want to do a million IP addresses on that router, so I just put a switch in the middle instead. So I'm not actually using the internet router in Topology. I'm just going to send it out to a new window and drag it over here. Unless I actually need it to demonstrate something, which I don't think I will. So why is that? Okay. Cool, so let's look at our neighbors here. Yep, we got plenty of neighbors here. And when we do OSPF over the DMVPN, I'm going to start caring about who the DR is, and I'll explain why later. But in the underlay, just because this is all on one multi-access segment, I don't care who the DR and the BDR is, because they should have, they do all have reachability to each other. So we'll wait for, see, 25 got elected, the DR there. So we'll see. All right, cool. So
I got one more question about what is the underlay. So the underlay, if I try to explain it, is basically like just the physical network on top of which you build these tunnels, the tunnel virtual topology. Mm-hmm. Yeah, so he's using OSPF to create connectivity in the underlay, although they're directly connected, so there is connectivity either way. But
so if you're studying for your CCNA or something, and you're doing packet tracer labs, what you're configuring is the underlay, assuming you haven't gotten to tunneling yet, which I don't think you have. everything you're configuring is going to be the underlay, right? Your vanilla OSPF, IP addresses, routing, all of that fun stuff. All that's going to be in the underlay. The overlay is when you start building these virtualized tunnels over the network that use the underlay for its transport. So you can think of it as sort of a tiered system where, like for example, if you think about, I'll use an analogy, or I'll try to use an analogy. It's not a perfect analogy, but maybe it'll help you understand better. If you think about like the highway system, right? You've got the ground, right, that you build the highway on top of. So the highway in this context is your overlay, right? The highway can wind and curve all at once, doesn't affect the ground underneath, but the ground underneath is supporting the structure of the highway. It's the same in this context here. We've got the underlay network, which is supporting the overlay tunnels, but the overlay tunnels can go whichever path they want, independent of the transport path. So I hope that analogy gives a good visual picture for it. So let's see. Cool. We've got all the loopbacks here. Okay. So the configuration here, I'm going to start off without encryption, and then I'm going to incorporate IPsec, because there are some IPsec-specific details we'll have to discuss at that point. So I'm going to use tunnel 0. Now, first thing we're going to do, there's a couple things we're going to do here. We're going to give this an overlay IP address. Now, again, this is the overlay. This is the IP network of the tunnel. So we're going to have to pick a subnet that we're using for the DMVPN. Let's use 172.16.0. We'll do 11. Cool. So that's that. And I should mention here, we're starting off with phase 1. So DMVPN has 3 phases to configure. Each of them is sort of an incremental improvement on the other. Phase 1 and phase 2 is a bigger jump than phase 2 to phase 3. So phase 1 is just going to be pure hub-to-spoke communication. So with phase 2 and phase 3, you can have the spokes dynamically build tunnel scheduler, and we'll talk about how that happens. But in phase 1, which is the original DMVPN phase, we're just doing hub-to-spoke communication. So if the spokes want to talk to each other, they can't go directly to each other. They have to all get punted through a hub. So the flow would go spoke, hub, spoke, and we'll take a look at how that works when we actually implement this. So on the hub here, the configuration is going to be starting off with the overlay IP address, and then we have to configure the tunnel mode. Now, by default, and I should let's see if I can do a show run all here, and let's see if they'll show it. Tunnel mode GRE IP. So this is the default mode for any tunnel interface you create on a Cisco router. It's going to be this GRE tunnel. But again, the problem here is that the GRE IP, the default, assumes point-to-point GRE. And that means that in practice, we would have to specify both a tunnel source and a tunnel destination in order for the line protocol and the tunnel to come up. Otherwise, it wouldn't. Now, so I can demonstrate that actually. So we're going to use the loopback here as our tunnel source. And you can see the tunnel remains down. At this point, I would have to configure a tunnel destination. What is there to configure? Don't worry about the dynamic. The dynamic is something different. The solution we're going to use here to the problem is GRE multipoint. So once I configure tunnel mode GRE multipoint, we should see that the tunnel comes up. Right? Now, this doesn't mean that the forwarding is actually going to work. What this effectively means is that I just removed the requirement for there to be a tunnel destination. And it's basically forgiving me for not having it there. And the other thing here is I'm going to configure as a tunnel key. Now, a tunnel key, if you haven't worked with GRE extensively, might be a unfamiliar concept. What a tunnel key does is it's encoded in the GRE header. And the idea is that if you have multiple GRE tunnels on the device that are terminating to the same destination and from the same source, it would be impossible to distinguish between the tunnels there. So you specify a tunnel key, that becomes a good distinguisher. So when we do Flex VPN, we might have a case where we have multiple tunnels that are using the same source and destination. So I'm specifying a tunnel key ahead of time just to avoid any potential mix-ups there. So that's that. This is all the configuration tunnel-wise that we have to do. Now, the next thing that we're going to configure is going to be our NHRP stuff. Now, NHRP, again, is the protocol that we're using to actually build the DMVPN fabric. So do the registration of the spokes, do the next hop resolution to resolve the underlay or NBMA destination IP address there. It does a lot. Now, there's a couple of commands that we're going to absolutely need in order to get this to work. The first command I'm going to run is network ID. This is absolutely required. Not much more to say about that. This command, the reason it's required is because this is effectively enabling NHRP there. The next step, you don't have to do this, I will, is to specify authentication. Just a generally good practice. So I'll specify DMVPN here. I normally use, because I'm normally doing DMVPN for CCIE practice, I normally use CCIE just instinctively as the authentication string, but we're not doing a CCIE stream here. And that's it, unless I'm forgetting something. If you look at guides, what you'll see is that they'll run this command here, and I'm going to run it. And what you'll see is where does command go? Now, as a general guiding principle, if you ever run a command on an interface or in any configuration mode, and then you go and do a show run and it's not there, chances are that was the default. And in this case, it is the default. So you'll see guides that explicitly point out, because I don't know if I have my timeline right on this, but the change of making this a default is fairly recent. So you'll see guides written from a few years ago that will tell you run that command explicitly, and it's always a good practice too. In fact, I end up always doing it. But it is worth it to note that if you do it and you don't see it in your config, don't panic. If you do a show run all, you can see, and I'll leave that as an exercise for the viewer there. But if you do a show run all, you'll see that it's there. What this does, and we'll talk about the way the mapping works here. This is basically how we run multicast traffic. So if you've looked at the routing protocols, EIGRP, OSPF, BGP is the exception here, but EIGRP and OSPF, the way they form their neighborships is they use multicast hellos. And if you don't specify the multicast mapping, DMVPN effectively won't know what the destination IP address for the outer header is. Because even if your inner packet is multicast, which it would be for something like a hello packet for OSPF, which would use 224.0.0.5 for the destination on the inside IP header, when you do the GRE encapsulation and then put the outer header, you still need a unicast IP address on the outer header there. And so the mapping command here is going to specify what IP address you use in order to get that to work, in order to get the multicast traffic to the hub. And that's the thing to know about the DMVPN here, is that multicast traffic always, because of that pesky little detail there, is always going to be hub to spoke. You have other kinds of traffic like the unicast where you can do resolution and get spoke to spoke in the later phases, but multicast traffic, no matter what phase you're using, is always going to be hub to spoke in DMVPN. That's why all your routing relationships are hub to spoke, which we'll take a look at later. And then on the hub side, we're using dynamic because the idea is that we're going to be receiving the multicast traffic from the spokes. So we're going to dynamically create those mappings as the spokes come in. So that's that. We'll add more commands later, but this should be enough to get this working. I have a very bad habit of leaving off, because you can tell it's a number of commands here, and the list will grow as we move on to the other devices and as we add more concepts in here. I have a nasty habit of forgetting one or two commands, and if you forget one or two commands here, it's not going to work.
Just copy and paste it.
Yeah, and that's one of the things there where if you're doing a DMVPN lab like this, and I'm going to do that eventually here once I get to demonstrating it, copying and pasting it where you don't forget one of those commands is going to be integral to making sure that you don't spend unnecessary amounts of time troubleshooting something because you forgot a single command. So I shouldn't be doing this on the hub, my bad. We're going to go to one of those folks. We'll leave hub 2 for when we talk about dual hub redundancy. And I noticed a question in the chat because I have to stream open my laptop here. I noticed a question in the chat about hub redundancy. We'll get to that concept later.
Yeah.
We'll talk about optimizing it. For now, we're going to jump straight to one of the spokes here. And we'll look at, I'm going to shut the tunnel down because I want to be able to debug the NHRP when it comes time for it to actually do a registration. Now, when we talked about the configuration on the hub, we noted that, okay, well, this has to be GRE multipoint, right? And when we get to phase 2 and phase 3, we are going to configure multipoint on the spokes as well. But for phase 1, because you're always going to be going hub to spoke, you're never going to be going spoke to spoke. You do have a clear destination. That was the problem that we tried to solve with mGRE. But on the spoke side, we don't have that problem with phase 1 because all of the traffic is always going to go to the hub. So here we can just run a bog standard GRE tunnel here. So we configure our tunnel source 10.255.255.21, and before I configure the tunnel destination, I should ping if I can type source correctly, the address of the hub here. And this is just good practice. Now, in this context, obviously I knew that this was going to work, but it's good practice because if this doesn't work, then you have to do some troubleshooting before you actually try to get your DMVPN up. So we're going to configure tunnel source. Tunnel destination is going to be 10.255.255.11, which is hub 1 here. And then we're going to configure the overlay 172.16.0.21. It's going to use there. And then we're going to configure our authentication, DMVPN, network ID 1. And here I should note the order of the command doesn't matter. So here I enabled DMVPN and I configured the authentication. You don't have to do it in order. You can configure it in whatever order you want. It's just that without the network ID, NHRP isn't actually going to be operational. So at the end of the day, you're going to need that network ID command, but you can configure the operational parameters and then add that command to enable it if you so wish. So that's that. And then here we're going to have to add some extra commands. So the hub was fairly simple configuration-wise there. Here we're going to have to add a couple more commands because we have to tell the spoke to actually look for the hub. If you think about it, the hub is more of the passive receiver. In this context, it is the glue of the fabric, but the spokes are the ones that are actively reaching out, looking for resolutions, looking for registrations and things of that sort. So they're the ones that are going to actively reach out to the hub and form a relationship here. So we have to tell it who the hub is, and NHRP calls that the next hop server. And in this case, one of the most common mistakes with DMVPN is mixing up what IP addresses, because remember there's two IP addresses to worry about here. There's the underlay IP address, which is this 10.255.255 address, the thing we're actually sourcing our traffic from and destinating the traffic to in the underlay. And then there's the protocol, right? There's the overlay network, which is going to be this 172.16 network we're using for the tunnel IP. Now, there are some commands that are going to use this overlay IP, and NHS is one of them. There are some commands, like the map command, that are going to use the underlay, and you have to be very, very careful about what IP address you use, because if you mix them up, it's not going to work. So, very common themes here is going to be if you mix up any one of your commands, if you forget to implement one, or if you mix up what parameters you use, your DMVPN is going to work, and it's going to whine at you. So again, we're using the overlay address here of the hub, which if we go back to the hub here, we can see this is 172.16.0.11. So that's what we're using here, 172.16.0.11. Did I already run the, let's see what I've already done here. Okay, so there's two more commands we're going to have to do here. The first command is going to be dealing with the unicast reachability. So we're telling it, okay, to reach the hub, get to 172.16.0.11. The problem is it doesn't know what IP address to use there. Now, in phase 1, this actually isn't a problem because, as we'll see, it's just going to blindly apply this tunnel destination to everything. But I'm introducing this command now because in phase 2 and phase 3, we are absolutely going to need it. So what I'm going to do is do a map multicast here. And here you can see we're doing the IP NVMe address because we're saying all multicast traffic needs to be forwarded out some given destination. Right. And then if we're doing the unicast mapping, the IP address is a good destination. This is the overlay, which is going to be 172.16.0.11. And then IP address of the NVMe or the underlay, 10.255.255.11. So when we get to phase 2 and phase 3, this configuration is absolutely going to be necessary. Technically, you don't need it here because what's going to happen is no matter what the IP address resolves to anywhere else, including routing as a next hop, we're going to blindly apply this tunnel destination. What's it called? I could remove these commands here, but I'm probably just going to keep them there. But in effect, in phase 1, they're not going to really be doing anything there. Crap, I forgot to debug. So the point of keeping the tunnel shut down was that I needed to be able to debug the NHRP. Debug NHRP, my bad. So again, when this tunnel comes up, what it's going to do is it's going to use the next hop server overlay address that I provided here to actively reach out to the hub and form a registration. So let's do a no shut here, and assuming I did all the commands correctly, there we go. So we can see here, let's do a, we'll let it do a debug. Is it finished? Yep, looks like it's finished. So, nope. All right, so we look here. We have a registration request via tunnel 0. We're sending it out. Source is going to be 172.16.0.21. Destination is going to be 172.16.0.11. So this is using the overlay addresses here. And assuming I did everything correctly. What's wrong? Let's see. So here's troubleshooting fun. Let's see. What did I do wrong here? So let's see, I've got the loopback interfaces here. 172.16.0.21. Let's see, do I have the oh. Is it this way? Let's see. Show DMVPN. We'll do no shut here. Oh, there we go.
There you go. That's it.
Tunnel key. So again, it's using this as a distinguisher there. So if your tunnel keys don't match up, then it won't actually get through. Because from this hub router's perspective, it's using the tunnel key as a discriminator. So there's a couple parameters that need to match here. A lot of the parameters need to match here, and tunnel key is going to be one of them. My bad. So that's that. So the configuration here, now that we've got this on the spokes, effectively what we can do is copy and paste this over here and modify the parameters for whatever spokes we've got next. So all these map commands stay the same. Network ID stays the same. NHS stays the same. The only thing that changes is going to be the source here. And yep, that's pretty much it.
Yeah, got one question. Just to clarify the map keyword. So what does that IP NHRP map command actually do?
The map command, again, so we have two IP headers that we're worried about. The outer header, which is the header that we're actually using to route in the underlay, and then the overlay inside header. And this is going to be clear when we do packet captures. The map command here, the purpose is that we need to map this IP address here, and let me whiteboard this actually. So do I have my whiteboard still up? Yeah, I do. So if I whiteboard this here, what the encapsulation or the protocol stack is going to look like is we're going to have, this is the inside IP header. The inside IP header here. And we've got the source, which is going to be, let's say we're pinging from spoke 1 to hub 1. This would be 172.16.0.11. And then the destination is 172.16, my bad, it's 21, 16.0.11. That's what I was thinking of. And then we're going to do, we have our GRE header here, obviously. We have our GRE header in the correct color. And then we have our outside header here. Now, the point of the map command here is we know what our tunnel source is because we configured it locally. That's going to be our 10.255.255.21 address. What we don't know is in phase 2 and phase 3 what the destination is going to be. Now, again, I mentioned in phase 1, the map command isn't really necessary. I'm introducing it, so we have it in mind for phase 2. But if we ignore the tunnel destination, what this would do is it would look at this overlay address and say, okay, what do I need to put here that corresponds to this? And the map command would tell it, if I bring the console over here, the map command is going to tell it if we want to get to 0.11, we have to use this address in the underlay. So that's what it would do. It would apply this address as the destination. And then it would go on its merry way. Now, again, I'm going to reiterate this in phase 1. You don't need this because this is here. But if we were to axe it for phase 2, then we would need to know what address to use here, and that's what that map command would tell us. So hope that clears things up. So what I'm going to do here is make sure that this guy's registered properly. Yep. I'm going to go ahead and I'm not going to configure it on all the spokes. I'll just configure it on, say, 3 of them because I don't want to go through the hassle of removing the configuration anyway when we get to phase 2. So let's see our registration happen here. And we'll go ahead and I'll shut this interface down. We'll do a debug NHRP here just to see what's actually doing behind the scenes. So we'll no shut it in and let it do its thing there. So this is what's supposed to happen when you have the tunnel configured correctly. First of all, we've got the NHS being up. So this is effectively saying the hub is up there. And then what we're doing is we're sending a registration request out to the hub here. And then we're receiving a registration reply back in. So the reply is, in essence, what we're using here as an acknowledgement that the registration has been completed successfully. And then the way we would verify that on the hub side is the command I've been using while explaining it, which is show DMVPN. Again, this is basically the only command in iOS that's actually going to explicitly refer to DMVPN as DMVPN. Every other command is going to refer to one of its components. So there is a show IP NHRP command, for example, that we'll make use of later when we actually start routing networks over our DMVPN there. But if we want to see what routers have actually registered to us, we can do our show DMVPN here, and then there's a show DMVPN detail that'll actually, if we're running IPsec, it'll show us some of the details about the IPsec security associations there. Yeah. Now, the other thing to note here is, again, we're doing tunneling here. So we can run IPv6 here over the tunnel, and we may at some point later in the video. We can run IPv6 over the tunnel, and we don't need to run IPv6 over our underlay because it's doing the encapsulation. So we can encapsulate our IPv6 using GRE, and then encapsulate that GRE using IPv4. So GRE can encapsulate damn near everything. That's one of the amazing things about it. It is very generic in terms of what it can encapsulate. So we can encapsulate IPv6 on the inside, and then run the IPv4 as the underlay. So that's that, and I bring that up because I was reminded of it by the v6 indicator here. that's that. So that's phase 1 here. Now, if I want to reach, let's say, spoke 2, so I'll ping its IP address here, which is going to be 022. You can see that this is working, right? We do have reachability. And we can obviously, we're getting a ping message back. So we've got bidirectional reachability. But if we do a trace route, and then we'll do numeric, because I don't want to try to resolve it using DNS, you'll see here what's actually happening in the context of our topology is that it's doing this effectively. So it is, I should probably use a different drawing here that's not completely shadowed by markings. So we have hub 1 here, and we've got our DMVPN cloud. Spoke 1, spoke 2. I'll just worry about these 2 for now. What is effectively happening is you're going this way up to the hub and then back down. This happens for any spoke-to-spoke communication, no matter how many spokes we have. We're in phase 1, we're always going up to the hub and then back down. And the reason for that is just because when we're doing the tunnel configuration, again, we specified this tunnel destination here as being static. There is no other destination that this router would forward to over the tunnel. It's going to take all traffic at this destination as on the outer IP header and do the routing, which effectively means that, again, we're always going hub to spoke. Even trying to ping between spokes, we're going spoke hub spoke. That's how the traffic flow is working here with phase 1, and that's this primary disadvantage here. Is that phase 1 works? Sure, we have reachability, so spoke to spoke. It's just that the spoke to spoke reachability isn't actually direct spoke to spoke. It's, again, spoke hub spoke. So before we move on to phase 2, anything that we need to look at in the chat?
There was a question, what layer does this protocol operate on the OSI? How would you answer that?
It depends on who you ask.
Yeah.
So I don't know what you're referring to, because again, DMVPN is really just an amalgamation or a combination of
right.
different protocols here. So DMVPN isn't a real thing, is what I like to say to people. It's just a solution that combines different protocols. So it depends on what protocol you're asking about. If you're talking about NHRP, well, okay, the easier answer is GRE. GRE, I'm going to argue, is a layer 4 protocol because it has an IP protocol number. That's my argument for why. Actually, let me see if I can. I should have a DMVPN packet capture here that we can take a look at to defend my point here. So the way the GRE encapsulation is working here is that it's encapsulating. No, I don't want to show your update, Wireshark. It's encapsulating the IPv4 inside GRE, and then we've got the outer header here, and it's got an IP protocol number because it is the immediate next header after the outer IP header. So I'm going to argue it's layer 4 based on that. Now, if we look at the NHRP here, we can see that this is actually directly getting encapsulated by GRE here. So I don't have a good answer for what layer this is. If you talk about its function, I'm going to argue it fits into layer. I would argue it's a. That's a good question. I'd argue it's an application. I've never actually thought about it before.
Yeah.
That's why I'm thinking a little bit here. I'd argue it's an application and its function. But if you were to look at this packet capture and say, okay, well, what layer is this? That's where it gets a little more muddy. Donald says layer 4. Yeah. OSI is OSI. So I'm going to argue layer 7. Yeah.
Fair enough.
Any other questions we need to look at?
Oh, we just got another one. In ST Access, what is different between VXLAN and DMVPN? So DMVPN is not part of ST Access. This is a different concept.
DMVPN is your WAN, right? So you wouldn't be using DMVPN and SD access isn't exactly a fair comparison there. If you wanted to compare DMVPN and SD-WAN, then we could have a discussion there.
Yeah.
A discussion that would happen after the stream. But you could have a discussion there. But SD access is for building a campus overlay, and DMVPN is the traditional way of building a WAN overlay. So they're two different concepts there, and they're not mutually exclusive.
Yeah. So SD access more the LAN side, campus, LAN, DMVPN for WAN, connectivity between campuses, between sites. Yep.
Okie doke. Cool.
All right.
So now we've got that out of the way, we can take a look at phase 2. Phase 2 is where things get a little more interesting. So phase 2 and phase 3 are both the direct spoke-to-spoke phases. These two are the phases where we can actually have the spokes build direct tunnels to each other so that we can avoid this, where we're hairpinning all the traffic through the hub and then forcing it back out that way, right? No matter how many times I do this, it's going to be spoke hub spoke. So phase 2 is the start of how we can avoid that. And phase 3 is just really an incremental improvement to make phase 2 more efficient. So what I'm going to do is I'm not going to rip out the tunnel interface here. Let's do it. I'm just going to copy paste at this point, because we've already got a lot of the basic configuration down here. So I'm just going to copy paste, so there's no real harm in nuking the tunnel interface there. It's going to make it simpler here. So what we're going to do is we're going to, first of all, access destination command on the spokes, and then change this to what we had on the hub, which is GRE multipoint. And for phase 2 there, the primary change is going to be on how we configure the spokes. So again, firstly, we change this to GRE multipoint, keep the source the same, NHS is the same, and all that. And yeah, so let's go ahead and paste this in. So if I had configured phase 1 without these two, it would have worked, but then I would have had to come back in and add it anyway in phase 2. So let's do this real quick. Blah, blah, blah. Let's change this. And again, you can see, even though we didn't specify a tunnel destination, because we said GRE multipoint, it's foregoing the requirement of having a routable destination and then just relying on NHRP to do next hop resolution to figure out what the, I should I copy the entire thing, whatever the outer IP address is going to be. So let's do this, and then we'll go ahead and configure spoke through this. Now, because we are going to be keeping fundamentally the same base config, I'm going to go ahead and configure spoke 4 and spoke 5 with this configuration as well. And again, once you get this configuration built, you change some minor values. Like I'm changing like 2 numbers here, 2 digits here. I should write config T here, and effectively we can just copy paste this cookie cutter config.
Yeah.
So this is very easily automatable. Is that a word, automatable?
I think so.
This is very easily automatable. So if you needed to deploy a couple thousand spokes there in your DMVPN, you could very easily automate this configuration, because you would use an F-string or a Ginger template or whatever you would use to vary these numbers here, whatever you want to use in your automation there, whatever solution you're using. You would just change these values here, and the majority of this, because it's the same hub, is going to be kept the same. So if we do a show DMVPN on the site, you can see the hub hasn't really changed. What does change is that now we're using GRE multipoint here. So if I trace route to, first of all, let's ping to, we'll pick a new hub this time, 24, because it's the spice of life, or variety is the spice of life, rather. So we ping the spoke 4.
I think 24 is the spice of life.
Is it? So we're getting our reachability here to spoke 4. My trace route. I'm gonna have to pick a new spoke. Let's do spoke 5. We'll wait here. So you can see here, we're not going to the hub anymore. We are going directly to the spoke. Now, let's go ahead and debug our NHRP to figure out why that's actually happening. So what have I not tried so far? I've tried 4 and 5. Let's try 3. Let's figure out what's happening with 3 here. So firstly, I should note that if we do a show IP or show Ceph adjacency or show adjacency rather here, we can see that we've got adjacencies here. If I go ahead and do 23, we get a whole block of NHRP debug here, and then finally we've got the output of the trace route finishing here. Now, crap, I probably should do a pack capture. Let's do a pack capture off of spoke 1. So we'll do pack capture right there. What's the spoke I haven't tried? 22, I think I haven't tried. Okay, so I'm gonna go ahead and download this pack capture here, NHRP. Let's get in here. Okay, so resolution request, this is what I'm looking for here. So let's see, it should be in the blah blah. I'm looking for where it's actually asking for the mandatory part. There we go. That's where it's asking. I missed it. Okay, so this is the resolution request. You can see that it's being sent up to the hub here, 11, because this is our. We look at our spoke 1 here. We go to tunnel 0. The NHS is 172.16.0.11, and this maps out to 10.255.255.11. So this is what it's actually sending the resolution request. Is sending it to the hub. And sourcing it obviously from our tunnel source here. And you can see let's zoom in here to help you see it better. What we're doing is we are saying, okay, here's the destination protocol address. So this is what we're actually trying to get to. Here is our protocol address here, and here's our MBMA address, right? So this is all the boilerplate info that it needs in order to actually do the resolution. There's some other information here. There's a bunch of extensions to NHRP, but the key here we're actually looking for in this context is going to be right here in the protocol address. Now, if we look at the reply here, blah, blah, there we are. So I haven't looked in an NHRP pack capture in a while, so bear with me. So under the client information entry here, what we've got is the client protocol address, which is 22, and we've got the client MBMA address. Now, notably, the thing to note here is that this resolution request or reply rather, is coming straight from spoke 2. So spoke 2 is directly responding to spoke 1 with its information, and this is where it's gleaning all of the MBMA and protocol information off of. So we've got the underlay IP address here of 10.255.255.22. And so now, if we do a show IP NHRP, we can see that the spoke 1 here has learned the MBMA address for spoke 2, and it can go ahead and directly, directly send traffic to it. So that's why when we're doing our trace routes here, we can see we're no longer going to the hub, because now we've got the NBMA address here that's able to send traffic directly to. Now, if we were to run routing over this, so let's go ahead and run routing over it, and we'll go ahead and route some networks over, and we'll see how this ends up working when we're not just pinging the tunnel IPs here. So what I'll do is I'll go ahead and create a loopback here on the spokes, and this is going to be network connected behind the spoke, so you can consider this like the actual workstations and clients, in whatever case may be, that need to use the DMVPN. So let's say this is going to be 10.1.0.1. And okay, so there's 3 routing protocols that I'm going to end up talking about here: eIGRP, OSPF, and BGP. I guess you could technically run RIP and IS to IS, but no one does that. So we're going to talk about those 3 main routing protocols, and each of them in this context are going to have their own intricacies. So let's talk about routing with eIGRP first, because that ends up being Cisco's recommendation. eIGRP. You can also run BGP, and you can also run OSPF, but OSPF I'm going to say for last, because OSPF is a pain in the butt over an overlay. And by the end of the stream, you're going to realize why you don't run OSPF over a DMVPN. So I'll do the same thing on Spoke 2 here. So create a loop back here. I'll create more as we need, but I'm just going to do 1 on each for now. And then what I'll do is I'll run eIGRP. So let's run AS100 here. Now, when we are configuring our network statements here to add interfaces to the eIGRP process, we're just going to go ahead and configure the tunnel as part of it, and then we'll configure whatever other interface we're trying to advertise. All right, cool. Now let's go ahead and configure eIGRP here. Network, and then we'll configure our tunnel. So after this, in theory, in a moment, it should come up. So let's wait, and wait, and wait. Now, eIGRP is very fast about forming neighbors. So in a simple design like this, if it's not forming within a few seconds, you're doing something wrong. And in this case, right, if you think about how multicast is actually going to flow here, because again, when eIGRP forms its neighbor relationships, it's using a multicast hello. So, you might think, okay, well, we've enabled eIGRP, right? We do our show IP eIGRP interfaces here. You can see we have configured our interfaces to work in eIGRP, so it should be working. But if we think about, let's go back to our tunnel configuration here. So let's go back to these map commands here. Right, when we create these map commands, what we said is, okay, if you have multicast traffic, which an eIGRP hello is certainly multicast traffic, then we're going to use this as our underlay address. This is the hub. So what's effectively happening here is because Spoke is punting all of its eIGRP hello packets to the hub, and it's never making it to Spoke. And I alluded to this earlier, routing relationships in the context of a DMVPN will always be a hub to Spoke. You're never going to form a routing relationship between spokes, right? All of your routing is going to be learned from the hub in the context of the overlay routing. So when we actually get to the hub here, we don't have eIGRP configured, so what's happening is all these hello packets are getting punted straight up to the hub, and the hub is saying, I'm not running eIGRP, so I'm not going to do anything with them. And so all of these hello packets are getting punted to the hub and dying in deep space somewhere. So what we need to do is we need the hub to also participate in our routing. And this is where also this router being a hub, the glue of the fabric comes together, is that when we actually start to route over the fabric, we need the hub to essentially disseminate this routing information. So let's go ahead and go on here, and we're going to go ahead and enable the tunnel here. And you can see we've got our adjacencies up. Now, here's the fun part. Let's go ahead and look at this. We'll look at that closer later. So you can see, oh, well, it looks like we can look at this now. So let's go ahead and look at this, right? So we're looping here. So we've got an adjacency up, then it goes down, then it goes up again. So let's look at why that is. And this is one of the most common mistakes when you're learning DMVPN here, is you're going to form routing adjacencies and you're going to wonder, well, gee, why isn't this working? Well, and you can see we're continuing to flap our EIGRP neighborship here. And this error message here is going to tell us a lot about what's happening. Now, reading this, it sounds like a lot of gibberish, right? Mid-chain parent maintenance, all. What the heck is this? What's actually happening here is looks like we're routing the underlay out of the tunnel. So what we're effectively saying is, okay, you can reach the other device on the tunnel by going through the tunnel. Well, you might look at that and say, well, no crap, right? Thanks, Sherlock. But what this router is effectively trying to do is it's trying to route the tunnel through itself, which breaks it.
Yep.
That's what this is effectively saying. Now, we've got, and the reason for this is because what it's doing is it's learning the underlay address over EIGRP, which is a problem. Now, there's a couple ways that we could try to alleviate this. So show IP EIGRP interface. What we could do, actually, I don't know why did I forget to specify a wildcard mask here? I don't even know why we're advertising, because I specified the wrong loopback, that's why. So I accidentally advertised the underlay, but that's proof of what can happen here. I copied the wrong loopback. And I do the same thing on this guy. Whoops, wrong configuration hierarchy. Nope, I did the right thing on this guy. So in theory, in a moment here, this error message should stop. But this is what can happen here, is that when you're advertising the underlay address over the overlay, what's happening here is it's basically a fight for AD, right? So EIGRP has an AD of 90, OSPF has an AD of 110. In a fight for the routing table, EIGRP is going to win by AD, which is a bad thing for us because OSPF is disseminating the correct information. EIGRP is saying the transport for the tunnel is reachable through the tunnel, which again breaks the tunnel and brings it down. But the second it brings it down, the EIGRP adjacency is gone. The OSPF routes come back in the table, and now we've got properly working topology again, at least until the EIGRP neighborship comes back up. And then now we've got flapping, right? Because EIGRP is going to win the fight again, and it's going to go down, and then OSPF is going to take over again, and then EIGRP is going to come back up, and then the cycle repeats, right? That's where this flapping is coming from. So if you see this mid-chain parent maintenance for blah, blah, this error here, loop chain attempting to stack is your key error here. That's basically saying it's trying to loop the underlay reachability for the tunnel back inside the tunnel, which is a bad thing, right? As we saw here, we effectively let the whole time expire. So that's that. So we should have a stable topology here. If we go back to our routing table here, you can see we're not actually learning any routes. Now, if we go to our hub, we've got our routes here, right? Our 10.1, our 10.2 route, we've got that there. But if I do a show IP route for 10.2.0.0, it should be in this table, but it's not, right? So you might say, okay, well, maybe the spoke's not advertising the route, but it is advertising the route. The hub has it. So it's nothing that we've done in the spokes here because the spokes are advertising their routes. It's the hub that's not advertising them back around. Well, why is that? Well, if you think about what EIGRP does, when you have a route coming in an interface, right, it applies the split horizon rule. It says, okay, if you've got a route coming in an interface, in order to prevent loops, you can't advertise it back out the same interface, which makes sense normally because, well, if you are advertising, if you're getting a route from an interface, well, you would assume that whatever peer on the other end has that route array, so looping it back around isn't a good idea. So you split horizon to prevent some pretty nasty routing loops there. But in this context, that's a really bad thing because we've got both peers living out of the same tunnel interface and they're relying on the hub to learn routes. Not the best thing. So what we need to do here is disable EIGRP split horizon. So I go to EIGRP 100, or the tunnel here, and then no IP split horizon EIGRP 100. Careful not to just use IP split horizon. You gotta remember there's two protocols that use splitterizing eIGRP and RIP. If you just do this and hit enter, you're disabling it for RIP, not for eIGRP. So you have to make sure that you're specifying eIGRP and then your AS number. And as soon as you do that, you can see the tunnel interface resyncs. And boom, we've got our routes now. Okay, so let's go ahead and trace route to, or ping 10.2.0.1 source from 10.1.0.1. And look, we've got reachability. We've got reachability to the networks behind each spoke. Let's do a trace route. Numeric. Okay, so you see we're going spoke hub spoke. This is normal at first because it has to do a resolution. Let's keep doing it. And in theory, in the DMVPN, if you keep going, if you keep sending traffic, it's going to revert to spoke to spoke, direct spoke to spoke. But I'm doing it a lot of times here, and it's not wanting to work. It's not wanting to go spoke to spoke. So there's a lot of pitfalls here that you can fall into, and this is the last pitfall for phase 2, I promise you. So if we look at the route here, what it's actually saying, it's saying, okay, we've got a routing entry here, and this is the IP address. This is the next hop IP address that it's telling it to use. Who knows about this? This is the hub address, right? We've got, if we do a short interface brief here, this is the actual hub address. So the reason we're never transitioning away from the hub to spoke communication here, as we were promised in phase 2, is because the next hop is telling it to traverse the hub first, right? It's never going to have an incentive to try to resolve the spoke. It is the spoke's responsibility in this context to resolve the other spoke. So if it keeps sending that traffic to the hub is not going to say you should probably send it to the spoke. That's phase 3. That's the improvement with phase 3. But with phase 2, what you're going to end up having to do is have each of these routes and their next hops point directly to the spoke. So the way this is, and the reason that this is a problem here in the first place is because the hub, when it's re-advertising the route back out, it's setting the next hop as itself. So if we look at the routing table here, right, we can see that the next hop here is appropriate, right? For 10.1, we've got a next hop of the spoke. For 10.2, we've got a next hop of the respective spoke. The problem is that when the hub re-originates the route and re-advertises it, it's resetting the next hop to itself. So what we want to do is set the next hop self parameter, so known IP next hop self for eIGRP 100, and this should also flap the adjacency here. So you can get back up, and now if we go ahead and look at our route, we can see show IP route 10.2.0.0. We can see, boom, we've got our spoke addresses here, right? So now, notably, you should see it's still from 0.11 because it's still recognizing that it's being advertised from the hub. But the next hop that's actually using, if we look at our Ceph table here, to distill all the information down, the next hop is going to be directly out this tunnel. So if we do a trace route, you can see now we're going direct spoke to spoke. Instead of some above here, which we were going hub to spoke, or spoke hub spoke as it were. Now we're going direct spoke to spoke because we're forcing it to resolve the spoke address. So that's that. That is the routing aspect of phase 2. So that's the big disadvantage here, is that you have basically no routing flexibility. You cannot do summarization, because if you do summarization, what you would have to do is you have to, let's say spoke 2 and spoke 3 are both advertising a route. If you wanted to summarize it, well, you can't have 2 next hops for a route. You wouldn't know which one to use. Actually, we would load balance between them, which isn't optimal because we need deterministic routing here. So you need a way to be able to assign the appropriate next hops to the appropriate routes. And in this context, the way we're going to be doing that is by separating these routes out. So you can't do summarization because that would add ambiguity to your routing, and you can't change the next hops. That is a pain in the butt. That is not in favor of phase 2. That's why phase 3, that's one of the big selling points for phase 3 here, is that when we're doing the routing, we have a lot more flexibility because we don't need the next hop to be the spoke. So let's go ahead
Just
and...
a question from me. Would someone ever just like configure DMVPN phase 2 and just leave it at that? Like, I don't need phase 3? Would there be any good reason to do that, or not really?
So there might be a good reason to leave it at phase 1. If you don't care about the spoke-to-spoke aspect, you could definitely leave it at phase 1.
Okay.
I can't think of a good reason to leave it at phase 2.
Okay. Yeah.
There may be one that I haven't thought of, but it's going to be so fringe that, for the most part, because phase 3 is just another command, and I'm kind of foreshadowing it here, because phase 3 is just one more command on the hub and one more command on the spoke, there's really no good reason that you would want to keep it at phase 2. You're giving up a lot.
Right.
Keep it at phase 2 when all you need to do to transition to phase 3 is run an extra command. So no, to answer your question, no, I wouldn't say so. But yeah, so we're seeing here that there's a lot of routing inflexibility here. So the solution to this, before we explore the other protocols very briefly, because they're all going to operate the same with the exception of OSPF there, where we're adding some extra intricacies. But fundamentally, when the routes actually get in the routing table, no matter what protocol you're using to learn them, you're going to have the same issue. So the way we solve this is with phase 3. Now, phase 3, as I mentioned, is just one more command. So on the hub, our command is IP-NHRP redirect, and I'll get more into what this does later. So this is not a default command. You actually have to specify it. And then on the spokes, it's IP-NHRP shortcut. And if I do a show run here, you'll see it doesn't show up, right? There's no shortcut command in sight. And what this alludes to is just this is a default. So redirect is not a default, but shortcut is. But you need both in place in order to operate in phase 3, because you need the hub to send redirects and then you need the spoke to use them, and that's the point of the shortcut.
So to activate phase 3, it really is just that one command on the hub?
Yeah, it's just redirect. Assuming you're running on a platform that considers shortcut at default. It's the same as multicast dynamic. You'll see some guides that recommend that you run it discretely, or I'm sorry, explicitly rather, because shortcut was not always a default parameter. But on the modern platforms it is. So that's really all I have to do to configure phase 3 routing. So now what I'm going to do is I'm going to reconfigure next hop self on this guy here. Now I've configured phase 3. If I go here to mGRE, firstly, you can see that we've got the route still, but we've reset the next hop. So instead of it being 22, now it's back to 11. Then we're going to trace route here, source 10101 numeric. So we're going hop to spoke, and in theory, boom, spoke to spoke. Now, this is slightly different because in phase 2, what happened was immediately when we ran the trace route, it was spoke to spoke, right? When we ran the trace route, you can see star here because it was trying to resolve the spoke, but afterwards, immediately spoke to spoke here. Here, we are going hub to spoke at first, and then when we do another trace route, it goes spoke to spoke. And the reason is how phase 3 works. So the way phase 3 works is, firstly, you're routing the traffic to the hub, right? That doesn't change. So if we look at the routing table entry here for the spoke route, this is still pushing it to the hub. That doesn't change. You're still routing the initial stream to the hub. But if you think about ICMP redirects, and it's a very similar concept, if you think about ICMP redirects, the way it works is if you are routing traffic out of the same interface that you're receiving it, in other words, if there is a more efficient path rather than hairpinning the traffic through a single device, that device is going to send an ICMP redirect that tells you, okay, there is a better next hop you could be using, there's a better gateway you could be using, here's the IP address that you should be sending stuff to, right? NHRP redirects, or the formal name is NHRP traffic indicators, work the exact same way. The hub is going to get this traffic, it's going to do the routing, and the hub is going to be able to do the appropriate routing because it has all of the original routes, right? It knows where the next hops are. But if you'll notice, the traffic comes in tunnel 0 and gets routed out tunnel 0. NHRP at this point realizes, crap, this is going in from the same DMVPN, out the same DMVPN. So at this point, now it's sending a traffic indicator to tell spoke 1, hey, look, I know you're sending traffic to me, and that's cool and all, but you could be sending it straight to spoke 2. So go ahead and try to resolve spoke 2. So what I'm going to do is configure mGRE on this guy here, because I'm going to go ahead and show how that resolution process actually ends up working. So if we go here, 023, and then I'm going to configure this as well. So let's go ahead and so we can see we've got our mGRE adjacency up here. Let's see here. So if I go to spoke 1 routing table 10300, we have our route. Notably, the next hub is the hub, not the spoke. But what I'm going to do here is a couple of things. First, I'm going to start a packet capture on spoke 1. Secondly, I'm going to debug NHRP here, and then I'm going to try a trace route again. Whoops, wrong guy. So now I'm going to spoke 3. And we've got a lot of debugs here.
Yep.
Now if we on that, you can see we've got a resolution request in queued for destination 10301, and I'm looking for something very specific here. Receive traffic indication is up here. I missed it. So what happened here was the spoke 1 here sent the traffic to the hub. The hub routed it out, doing its own thing, because from its perspective, it's just doing routing. So it routed out the tunnel. But at this point, the hub's logic kicks in and says, okay, well, wait, I just received traffic in tunnel 0 and routed it back out tunnel 0. So what it does is it sends a traffic indication here to spoke 1, effectively telling it, hey, you can resolve the spoke directly, and that's what it ends up doing. So it sends a resolution request here. So it queues a resolution request and then sends a resolution request out here to 10301. You can see the NVMe address here is going to be 11, which is our hub. And then see if there's any other debugs here that are going to be insightful. No, not quite. So what we'll do is we'll take a look at the packet capture instead. So I'm going to go ahead and save packet capture here, and we'll take a look at this. So NHRP, you can see this is our traffic indication. So it includes the packet that actually causes the indication, which is kind of cool. So this is the actual packet that caused the hub to send the indication to the spoke. And at this point, what ends up happening here is that the spoke sends a resolution request up to the hub. You also see that the hub is sending one to the spoke. That's because both spokes end up sending resolution requests to each other. So we've got that here. The spokes are going to try to resolve each other, but for our purposes here, what's relevant is this resolution request right here. So we're looking at destination protocol address, which is 10301. The hub is going to do a route lookup on that and figure out that it needs to go to spoke 3, because the hub knows that the 10301 address goes out this way. So it's going to know what spoke it needs to send it to. So at this point, the resolution request goes to a spoke, the spoke responds, and everything's hunky-dory, right? So we've got a resolution reply coming from 23, which is spoke 3, to spoke 1. And at this point, the destination protocol address, if we look at the client entry here, the protocol address is 023, the NVMe address is 23. So that's how the spokes end up resolving each other in phase 3, is that instead of having to keep the next hop fixed so that it immediately does a resolution, we're saying, okay, it's okay if you send the hub the traffic initially, but the hub is going to come back around and say, you need to resolve this spoke directly so that you stop sending your traffic through me and you build this dynamic spoke-to-spoke tunnel. That's what we've been striving for in this entire solution. It's building a direct spoke-to-spoke tunnel between spoke 1 and spoke 3, whatever two spokes are communicating are, so that we can send the traffic directly over the underlay instead of having to bother the hub with it. That's the outcome that we've been striving for. So the other thing here, before we cover the rest of routing, and then we'll cover IPsec, and I think we'll call that wraps there. Unless we have time to talk about the optimizations. The other thing that we're going to have to talk about here is, now that we've got phase 3, again, we can keep the next hops the same, and effectively what this is going to do is, oh, well, I'm looking at the wrong router, my bad. So if we look at our NHRP routes here, we can see this percentage sign means it's actually done a next hop override. So the next hop here is the same, but now it's done the resolution, it knows the real next hop. If we look at our forwarding table, which is actually what matters in forwarding, we can see that the next hop is not what we see in the routing table, it's what it resolved. So the routing table is saying, okay, the route is going to go out to the hub, but what's actually happening in the forwarding plane in the Ceph table is, because it's done the resolution for the protocol address of the spoke, it's installed that as a next hop override in the Ceph table. So that's that. Now, if we go ahead and take a look at this, my point here in showing the routing table was that we can see that these routes all have the same next hop. So the reason we couldn't do summarization in phase 2 is because these routes needed to have individual next hops. In phase 3, they don't need to have the same next hops, or they don't need to have the correct next hops. They can have the hub next hops. So what we can do on the hub side, let's go into the mGRE here. Actually, again, wrong thing, interface. We can configure a summarization. Now, a common theme here is that we can configure a default summary, right? Because we don't actually need the specific routes, because it's all going to have the same next hop anyway, we can just configure the route directly as a default route. And so now we don't have any of the client routes, but what we have is a default route. Now, what this also means is that we can turn split horizon back on, because now we're not actually advertising the spoke routes raw to the spokes. We are advertising a summary, and the summary is going to be originated from the hub, which means that it's not subject to split horizon. So even if I turn split horizon back on, and I look at the routing table again, we can see that we still have a default route. Now, in phase 2, this would have been a problem, because what this effectively would have meant is that the spoke-to-spoke traffic would have always been pinned through the hub, because it would have no incentive to do a spoke-to-spoke resolution. Now it does have that incentive to do spoke-to-spoke resolution. So we can do a trace route. Let's go back here. Let's see, does it still have that resolved? Yeah, clear IP NHRP. So I'm going to force it to wipe the cache so it does another resolution. So again, 10301, we don't have a route for it, but if we look in the Ceph table, what it's going to do is it's going to go out this next hop. So let's do a trace route. 10301, source 10101, and then numeric. So again, we're going hub to spoke. That's okay. What matters is that in the end, we go spoke to spoke. And if we go look at our Ceph table now, you can see it's now changed from the hub being the next hop in the data plane to the resolved protocol address being the next hop in the data plane. And if we do our show IP NHRP, we can see here that the MBMA address here in both this and this is going to be 10.255.255.23. So in the outer IP header, it's going to use this MBMA address. Now, let's go ahead and take a look at what I want to take a look at. The routing table. Because now we actually need a way to tell it from a routing perspective in the routing table, use list next hop. So previously, let's see if it's still saved up here. Previously, we had this % sign. That was the next hop override, right? So instead of creating a separate route, we overrode this route. Down here, because it's a default route, we split it out into an NHRP route, which has an AD of 250, right? So if I do a show DMVPN, you can see here, not only has it done a resolution of spoke 3, but you can see it's DT1. DT1 means that we've got a route installed. and T2. So if this was DT2, it would mean that we didn't install a separate NHRP route. So we're not doing summarization, but we did do a next hop override. So if I had done show DMVPN up here, it would have shown DT2 instead of DT1 for the spoke resolution here. And again, we just see the NHRP route because we have a summary, and it needs to create a separate route entry to describe what the next hop to this particular spoke network is. And if you're wondering how it knows this, because the question that a lot of people have is, well, how does the spoke know what the actual network is? It's just pinging one address, and the hub is not advertising a network through EIGRP. So how does it know? And the answer is that when it does the resolution, it's sending a resolution request directly for that network here. So you can see it's sending an NHRP resolution request for this destination. And so the spoke, when it does a resolution reply, when it responds to this request, it's going to include the information about the route and the subnet mask. And so that's what it's actually using to create the route here. Is going to be the subnet mask. And this metric here is always going to be 255. So all it needs is the network and the prefix length, and then it's going to be able to create the NHRP route instead of doing the next hop override. Because the problem with doing a next hop override here is that this is a summary. So like I mentioned, you might very well have multiple next hops, so you can't override the next hop of this route directly. You have to create a new route that you can then set the next hop on. And that's how this is actually working behind the scenes. And I'll leave doing a packet capture to actually show the routing information as an exercise to the viewer, but it's fairly benign. It's really just, it's telling you the network address and the prefix length, and then the router makes do with that. Any questions so far?
Nope, no new ones.
Okay, cool. So the other thing that I'm going to talk about here is BGP and OSPF.
Sure.
I'm not going to talk much about BGP because it's really just the same thing, with one exception. So BGP, typically when we configure BGP, so what I'm going to do is I'm going to axe my EIGRP here. So let's go ahead and do no router EIGRP, no router EIGRP, and I don't think I can figure it out on these routers here. So with BGP, typically how this works is you're going to be configuring your static peers, right? So on the hub side, for every spoke, you'd have to configure a static neighbor statement. That's a pain in the butt, a massive one at that, because that means that, when we were configuring EIGRP, right, if we wanted to add a new spoke, that configuration only had to be done on the spoke. We didn't have to touch the hub at all to scale out our topology. And that's one of the big advantages of DMVPN, is that we don't actually have to touch the hub when we add a new spoke. We just touch the spoke, and the spoke will handle all of the dynamic registrations to the hub. Problem here is with BGP, because we have to have static peerings, we'd have to have a neighbor statement for every single spoke, which means if we add a new spoke on, not only do we have to configure the spoke to onboard onto the fabric, now we have to configure the hub to form a BGP peering if we're choosing to use BGP over the DMVPN here. Fortunately, there's a solution to this. It's called BGP Dynamic Neighbors. And you might be saying, wow, I've never heard of that before, right? And if you haven't been invested in BGP, you probably haven't heard of it before. The way dynamic neighbors works is not how you would think it works based on the name, right? When you think dynamic neighbors, you might think about OSPF. OSPF sends out hello messages. It does its own negotiation. BGP dynamic neighbors is really more of, think about ether channel passive, right? When you have an ether channel and you set it to passive, what it means is that it's waiting for an active LACP peer to send in LACP to you before it sends one back out. So it's not actively looking for neighbors, it's just responding to an LACP channel request, effectively, if it receives one. This is the same concept here, in that with BGP dynamic neighbors, it's not actively going out and searching for dynamic neighbors. What dynamic neighbors means is it's not actively going to send out any open messages, but if it receives an open message, it will respond in kind. So just like LACP passive, you cannot have both sides be BGP dynamic neighbors. You can just have the hub be dynamic neighbors, and then the spoke has a static peering to initiate the peering with the hub. that's the essence of BGP dynamic neighbors. So you can think of it as LACP passive. It's the same logic pretty much. So the command here is going to be BGP listen range. So again, this is going to tell you a lot about what it's actually doing. It's just listening for hello open messages, which are the BGP equivalent of hellos, and then only responding in kind if it receives one. So listen range, and here you're telling it what subnet range it's going to listen for. This is the source range. Now, because we should be routing over the tunnel, we're just going to specify a tunnel subnet as our range, and then we have to specify a peer group, which is what it sounds like, a group of peers. So DMVPN is the name. Now I have to actually create the peer group, and then DMVPN will specify remote AS, say 100 here, and let's say, yeah, it should be all we need. Actually, no. Yeah, it should be all we need, actually, because we don't have to specify update source. So we'll go over here, BGP 100, and then we'll specify. Now, we can't do dynamic neighbors on this side, again, because that would be passive on both sides. So we have to specify our neighbor. And again, we're using the overlay IP here, remote AS 100. Router BGP 100, neighbor 172.16.0.11, remote AS 100. And you can see warning messages here. This star here means this peer was dynamically formed. And you can go to the show IP BGP summary, and you can see here total dynamically created neighbors 2, and then the default maximum is 100. And again, the asterisk here is going to be telling us that this is a dynamically formed peer instead of one that we've configured statically. So this is the solution to the problem I mentioned earlier, which is that BGP as the overlay protocol doesn't scale very well, where you would just configure dynamic neighbors on the hub, and now you're back to a similar system as you were via GRP, where you don't have to configure the hub every time you add a new spoke. You just configure the spoke to do a static peering up to the hub, and then the hub's got dynamic neighbors to automatically respond to any open messages that it receives, as long as it falls within the subnet, which it will, because that's our DMVPN subnet. So now we can just go into advertising our networks. So 10.1.0.0, and again, because BGP is pulling routes directly out of the routing table here, we need the masks to match exactly what we have them. And then 3. Now, the thing here is that the hub's going to receive all of the routes here, but it's not going to actually advertise them back out because of the IBGP split horizon rule, which says that we need to have a full mesh. Basically, if it receives an IBGP route, it's not going to advertise it back out to an IBGP peer. That's the IBGP split horizon rule, and to do loop prevention there. Now, if you were doing phase 2 of BGP, what you'd have to do is you'd have to configure the hub as a route reflector. So if I configure the hub here as a route reflector, neighbor DMVPN route reflector client, we see we're flapping the peers here, and in a second we should come back up because these folks are going to reinitiate their hello or their opens rather. So spoke 3 is back up, spoke 1 and spoke 2 are back up. So if I go to my BGP table here, you still with me, Jeremy?
Yep.
Okay, cool. My my CML connection went out there.
Oh, okay.
I don't know why.
Yeah, we're good. We're good.
That was something with my internet or something. So you can see here, we've got the route advertised because it's a route reflector. We're bypassing the split horizon rule, and now the next hops are kept original because we're not saying it to change the next hops. So this would be if we were using phase 2, we would set the hub to be a route reflector and call it a day there. But we're using phase 3. So screw that. What we're going to do, and again with phase 3, we don't need any specific routes. We just need a summary, right? Now, we could do that a number of ways. We could configure aggregation on this router here to do aggregate address, let's say 10.0.0.0, 255. Actually, I'm not going to do that. Let's say 10.0.0.0, 255, 255, let's say 248. I'm trying to make it so that we're not, because we have our actual underlay address is send 255. So if I just did a /8 here, we would have that stacked loop again, where we are routing a tunnel through the tunnel. So I'm trying to avoid that. So this should do a good job of that. So in the moment here, assuming I didn't boomer our aggregation command, I don't think I did. Let's see. Okay, well, that wasn't the point I was trying to make anyway. The point I'm trying to make here is that because we don't need specific routes, we can just do a default route out. And that would be the ultimate form here. If I do a Shaggy BGP, crack BGP, start out. There we go, we got a default route now. So if I go here to Shaggy route BGP, we can see now we're learning a default route just like we were via IGRP. And again, once we get the route in the routing table, no matter what protocol we use to learn it there, the routing operation for DMVPN is going to work fundamentally the same. So let me make sure I don't have this cached. So if we do a trace route again here, hub to spoke. If I do this again, spoke to spoke, right? So it's doing the same process, traffic indication, resolution request, resolution reply, all that fun stuff there. Now it's just through BGP, right? So we're just using a different protocol to do this. And you might want to run BGP over your DMVPN if you're obsessed with policy. So if you have a large DMVPN fabric there with multiple hubs, maybe you want to enforce routing policy, that you could use BGP to do that, and that would be easier than trying to influence the IGRP metrics. So that's a reason you might want to be using BGP there as your DMVPN routing protocol. Now, let's ask BGP. I've talked as much about that as I think I want to. The main thing there was just dynamic neighbors. Now, here's the pain in the butt. OSPF. Oh, Lord have mercy.
Looking forward to this.
Yeah. So, let's talk about the issues with running OSPF over a DMVPN. First one, if you're using, so this all depends on the network type, right? Which is already a great start. OSPF's viability over a DMVPN depends entirely on the network type, because the network types function differently. There are some network types and phase combinations that just straight up will not work. We're not going to look at those, obviously, because they won't work. We're just going to look at the ones that work and are at least remotely sensible. So that's one thing, is that you have to be careful with the network type. The second thing here is, let's take a look at the network type broadcast, for example, right? With network type broadcast, if you're using broadcast, that means you're electing a DR/BDR, right? So let's take a look at our painter here. So I'm going to go back. This diagram should work. So we're electing a DR/BDR. Okay. So earlier when I did my OSPF and the underlay, I didn't care who the DR/BDR was, right? I just said, okay, well, because these guys all have equal reachability to each other, and they did because they're all connected to a switch, they're all connected to a common segment, the DR doesn't matter because everyone has reachability to everyone else. But you'll remember here, with a DMVPN overlay, the only routers that actually have reachability to each other without having to resolve, for the purposes of routing, is going to be the hub down to the spokes, right? So the spokes, from a routing relationship perspective, don't actually have any reachability to each other, right? They're not forming direct routing relationships. So what this effectively means is that your DR has to be the hub, because the way the DR/BDR relationship works in OSPF is that you're forming logical hub and spoke. Your DR, and by extension your BDR, becomes the hub, and then all of your other routers, your DR others, are the spokes. And the only database exchange that's actually happening is with the DR and with the BDR. that is supposed to make things more efficient because you don't have all that flooding. But if your DR is a spoke, well, this spoke is going to try to exchange routes with that other spoke, which is going to fail. So we were introduced this problem of, okay, well, we need to make sure that these spokes are never elected as DRs, right? So we have to set priority 0. And if you're not careful, and you might be saying, okay, well, what if, maybe I don't set priority 0. Maybe I just bump this, because the default priority is 1. So maybe I just bump this to 255. And you'll say, okay, that's fine, right? So priority 255, higher priority, means it's going to be elected to PDR, or the DR rather. Here's the problem with that. The DR election in OSPF is not preemptive. If you elect a spoke, the DR, and that is a possibility if your hub happens to come into the DR election too late, and you didn't set these to 0, which is the only priority that outright bans it from the DR election. If your spoke happens to get elected to DR before the hub comes on the scene, oh, too bad. There goes your routing. Because now you don't have any database exchange going on because no one can reach that spoke except the hub, right? So if your hub is a DR other, the hub can get routes, the other spokes can't. So these spokes can't be allowed to participate at all. You have to use priority 0, because if you were to just say, okay, well, I'll just give the hub more priority, because it's non-preemptive, even if it has more priority, there is a very real chance that it won't be DR, and if it's not DR, again, poof, there goes your routing. Right? Which is that. Now, there are other network types that are less finicky than this, notably point-to-multipoint. Oh, but if you're using phase 2, point-to-multipoint doesn't work. Because, and this is a detail not a lot of people are familiar with, if you use point-to-multipoint, you're resetting the next hop, because from the perspective of OSPF, what this looks like is this, where the hub, and we've got the spokes here, and I'm not going to draw the, I will. So we're going to draw the DMVPN cloud here. The way that OSPF treats point-to-multipoint is that it's a series of point-to-point relationships on the same interface.
Yeah.
So point-to-point only works, only allows one neighbor on every single interface, which is a problem because we are terminating on a single tunnel interface here. So if you set point-to-point on your hub by accident, what you're going to end up seeing is the CLI go crazy because your neighbor relationships are going to start flopping rapidly. Because you've got spoke 1 trying to become a neighbor, then spoke 2 trying to become a neighbor, and if this is only allowing one neighbor, it'll drop this relationship, allow this relationship, then it's going to try again, and so on and so forth, right? You're going to get a large storm, and it's going to be very hard to stop because it's flooding the CLI with syslogs there. So you need to set this point-to-multipoint, which is going to treat this as a bundle of point-to-point links. Well, just like with mGRE where we had the next hop self, OSPF has a variation of that, where if you advertise a route up, it goes over one point-to-point link, effectively, one point-to-point circuit, and it comes back down another one, right? And then in between this, it's going to reset the next hop to itself. We already saw how with phase 2 that's a problem because that means it would have no incentive to do an ARP resolution. Phase 3, it would work because you don't need the next hop to be the spoke in order to trigger a resolution. You've got the traffic indicator to do that, but you don't have a traffic indicator in phase 2 because you didn't enable the IP and NHRP redirect command. So point-to-multipoint is one of those combinations where you cannot use with phase 2 if you care about spoke-to-spoke reachability. It will technically work. You will technically have routes in the table, but it's not going to afford you the benefit of spoke-to-spoke reachability. And at that point, why there's literally no advantage to using that compared to phase 1, right? Because all your traffic would be spoke-hub-spoke. So I hope I'm hammering my point here. This is a massive pain in the butt. I will configure it, but it's generally a very bad idea to use OSPF on your overlays. That's why Cisco's recommendation is the IGRP. But I will configure it just to show you what it looks like. So if we take a look at the tunnel, I shouldn't have any routing protocols up right now. What I'm going to do is configure on the tunnel and the loopback. First of all, I have to configure on the loopback IPsec network point-to-point. Now, this is phase 3, which means that it doesn't matter what the next hop is. So I could configure broadcast or point-to-multipoint. Either or works. I'm going to configure broadcast first, just because it's the easiest. So on the tunnel, the first thing I'm going to have to do is configure priority as 0, because this is spoken. I don't want it to be elected to DR. And then from here, I could go and IPsec, let's say 100 area 0, because I'm already using 1 for the underlay. So, and by the way, I'm using network point-to-point here because these are loopbacks, and if I don't do that, they're just going to get advertised as /32s. So IPsec priority 0. I don't want the DR election. And then IPsec 100 area 0. Int range tunnel, and then 101 IPsec network point-to-point. Sorry, OSPF priority 0. And then, oh, my bad. I'm getting myself mixed up here. This is correct. This is point-to-multi. This is IPsec network point-to-point. And then the tunnel is IPsec priority 0. Getting myself mixed up. Okay, IPsec 100 area 0. And then obviously the routing relationships are up to the hub, so we have to configure the hub. The hub needs to be elected to DR, so we can leave it at 1 because everyone else is going to bow out of the DR election. So here I should just be good directly enabling area 0 here. Oh, that's great. Huh. My router crashed. Fun.
Wonderful.
Yeah, I know, right?
That's the hub?
Yeah.
Oh.
So we'll wait for the
Wait a couple minutes.
hub to reload. I forgot to run a command. My bad. But yeah, going real well for the OSPF case there, eh?
Yeah.
Yeah. And that's one.
OSPF, it's a hassle to configure, and it makes your router crash.
Yeah.
Wonderful.
There's 2 other points there. Firstly, OSPF, because it's so intensive in terms of the SPF calculation, is going to, if you have a route reconvergence event, it's going to reconverge the entire topology, which puts strain on all of your routers. Secondly, it's really 3 points. Secondly, it's really easy to accidentally misconfigure. If you forget, like for example, on the point-to-multipoint I mentioned, if you accidentally set the point-to-point and you get a flap, I'm just going to force the hub to reload here because it doesn't look like it's wanting to reload on its own. If you don't do the proper configurations and you have it such that it improperly forms the neighborships there, you can get a very unexpected result. The third thing, and yes, there are 3 points. The third thing is that I talked about summarization with NHRP and BGP and how you could summarize down to a default. That's not a thing with OSPF because you can't do intra-area summarization. I have messed around with it. I've tried database filter. There are hacky ways that you can get summarization. What you could do if you wanted to is default information originate on the hub, and then you would do a distribute list on the spokes. That's the way I found that you can hack together sort of like a summarization if you want to on the spoke side. But OSPF intra-area summarization by default, if you're not messing around with dumb workarounds there, isn't really a thing. So you're losing out on part of the benefit of phase 3, which is that you can reduce the size of the spoke routing tables by just crushing everything into a default route. So that's the 3 points there. I'm going to elect not to do broadcast again because there's no real point. We know how OSPF broadcast turns out. It's just going to, on the spoke side, the routes will be learned because it's doing a database exchange, but it's just going to have the same next hops because broadcast doesn't change the next hops by default. So effectively, we would be reverting back to phase 2 behavior. And we would have no use for phase 3. The point where phase 3 comes in is point to multipoint, because you can have it reset the next hop, and then at that point you completely forego the DRBDR election. And from there, what you would actually do on the spoke side, while we're waiting for the router to reboot, because I'm not trying broadcast again, what you do is you'd have to configure spokes as point to point, because again, point to multipoint is just a bundle of point to point adjacencies. So from the spoke side, it is point to point because it's just neighboring up to the hub. But if you try that on the hub, and I'm not going to because it's probably going to crash again, if you tried that on the hub, it would flap the adjacencies over and over and over, because point to point only allows one adjacency. So while we're waiting for it to reboot, and again, once we do this, the priority command, because it just applies to the DRBDR election, the priority command that should be here somewhere but isn't. The priority command is going to axe itself, because it's not needed. It doesn't take effect in point-to-one because there is no DRBDR election for it to participate in. And I believe because it didn't save config, what this is going to end up doing is, all my config is gone. So give me a second. Curse OSPF. 10. What was it? 192.168.1 or .0.11. And then we'll run. So there is a way to get OSPF broadcast to work, just to be clear. But again, not really worth it. You lose a lot of benefits there. So let's go look at our routing table now, and then we'll go on the tunnel interface. I'm going to configure the tunnel again, GRE multipoint. We'll do tunnel key 1, tunnel source is 10.55.255.11. And then we'll do IP NHRP network ID 1, IP NHRP authentication, DMVPN, IP NHRP redirect. And that should be it. So if and the way this is going to end up working is I'm going to have to shut this interface here, just to see if it re-registers. And the reason that this that it failed originally is one of the other fun things about this, which is the MTU, right? So if we think about GRE is adding overhead to the tunnel interface, and actually what I should be doing is configuring the MTU to be some value lower than 1500 to allow for that overhead. So IP MTU, IP TCP adjust MSS, and then we lower this by 40. So this is the TCP maximum segment size. So I should have run that command on everyone, and that would have alleviated that issue. And you can tell because right before this crash, and you actually you should be able to see it, it went from X start to down. So if you see an adjacency get to X start and then go back down, that's a very good indicator that an MTU issue. And I'm just a dummy and forgot to set the MTU on the tunnels there. So ideally, you should be doing that. It is worth noting that the iOS will, from a data plane perspective, will automatically do an adjustment. So if I do no TCP adjust MSS 1360, and then I do a show run interface, or not show run, show interface tunnel 0. Blah, blah, blah. We can see, where's the MTU? So tunnel transport MTU is 1472 bytes, and it's accounting for the GRE header as well as the IP header, which together make up 24 bytes. You got 20 bytes for the IP header, and then 4 bytes for the GRE header. So from a data plane perspective, you don't need to worry about it. It'll fit in automatically. But it is still good practice to adjust your MTU even further. Logging synchronous. You want? I'm looking at your chat. I have logging synchronous on the devices here, but
yeah, it's on the console.
I need to re-add it to
right. Just
because
I
lost
rebooted.
the config. So teachers need to save your configs, kids. So
give us a write memory.
Yes, write mem, or just write.
There you go. Yeah.
So I should be able to, let's go ahead and do another ping towards 22. Okay, cool. So it's working. So if I do this, and I already changed good network type to point-to-point, but that is the reason it failed. Just for anyone who was wondering, because the MTU wasn't adjusted correctly. Now, it's like I have on tunnel 0 right now. Okay, cool. So what I'm going to do is configure this again as point to multipoint. And then I'm going to configure 100 area 0 here. Assume I'm not missing anything, or my router crash again. No, the adjacency should not come out. That does look correct. Let's make sure it's actually not coming up. Yeah, it's not. In brief, tunnel 0. So IPsec network point to point. We've got that correct. Oh, I know why. Timers. So again, when you configure DMVPN, if you're anything like me, you will forget a bunch of commands there. The thing to remember about the network types is that they change a lot of things, timers included.
Yep.
So point to multipoint has a timer of 3120 for hello dead. Point to point has a hello timer of 10, dead timer of 40. So if you don't have timers lined up, you're not going to get an adjacency coming up. So you can either change the spoke side or the hub side. I'm going to change the hub side. So hello interval 10, and this will automatically force the dead interval to be 40 because it's just an increment of times for the hello. And you can see now we've got the adjacencies
coming up.
So there's a lot of hoops that you need to jump through to get this to work. But if you get it to work, credit where credit's due, it will work. So we've got, and again, it's going to reset the next hop because this is point to multipoint now. So it's collection of point-to-point links. It's going to reset the next hop. But it's phase 3, so it's fine. But what we don't get, again, is the benefit of being able to do summarization. And it means that if there's any changing in network, we're not just reconverging on the hub. We're reconverging everywhere because we've got a shared LSDB. And we're recomputing SPF and everything. So that's OSPF. Again, fundamentally, when you get the route into the routing table, it doesn't matter what protocol you use, the routing is going to work the exact same way. So I could do, again, 10301, source 10101, numeric. So it's going to go hub, spoke, and then it's going to go direct spoke to spoke. And the reason is the same because the NHRP is doing the traffic indication, and then the spokes are doing spoke to spoke resolution. It's just that really OSPF offers no tangible benefits and isn't really worth all the work that it takes to get set up. So that's that. So that's the 3 routing protocols covered, and each of their intricacies. So again, with EIGRP, you have to be wary of split horizon and next hop self, depending on what you use. But EIGRP is, as we saw, the most flexible because it can do dynamic discovery, true dynamic discovery. It can do summarization into a default and all of that fun stuff. BGP, also a good option there. It's just that you have to be careful in terms of the peerings. But once you get that up, BGP has a lot of possibilities policy-wise. Same possibilities as if you were just running BGP. And then OSPF is OSPF. Don't use OSPF. Unless you're lobbing for the CCIE. That's the one thing. Unless you're lobbing for the CCIE.
You have to know all 3?
Yeah.
Yeah.
They will test on NHRP, OSPF, and BGP. Yeah. In the objectives, they call that out at least.
Okay.
But yeah, so be careful of that. So I'll cover two more things, and then I think we'll call it maybe three more things. So I think we'll call it a wrap here.
Sure.
The first thing that I'm going to cover is hub redundancy. And I'm not going to implement this to much extent, I don't think, because it's fairly straightforward and there's a lot of documentation on it if you want to go look at it further. So in DMVPN, there's two options for hub redundancy. There's dual hub single cloud and dual hub dual cloud. So what those options effectively mean, I'll delete this layer here. So now we're introducing the concept of, okay, well, the hub is the next hop server for our NHRP. So if the hub goes down, the glue of the fabric falls apart. And now we don't have, in technical terms, we don't have the next hop server to be able to resolve the next hop. So effectively, the entire fabric falls apart because we don't have a way to resolve the NBMA addresses from the overlay protocol addresses. So in any respectable DMVPN environment, you're almost certainly going to have at least two hubs that are serving the same DMVPN cloud. So we've got spoke 1, spoke 2, and then spoke 3. And we've got these guys wired in here. Okay, now there's two options here. You can do dual hub single cloud, and this is what I'm demonstrating here. So dual hub SC, single cloud. And this is referring to the fact that we've got one DMVPN tunnel that's operating, that both hubs are serving. So how this would look on the spoke side is we would configure, I did not mean to open Spotify, I meant to open Secure CRT. So if we look on the tunnel interface here, we configured map multicast and then the unicast map. What we would end up doing if we had two hubs is we would go on here and configure another set of maps, 10.255.255.12, and then map 172.16.0.12 to 10.255.255.12, and then we would configure another set of next hop servers. So you can see these commands are not mutually exclusive. They will take both of them. And so like if we have multicache traffic, for example, it's going to get replicated to 11 and 12. And then we're using both of these as our next hop servers. And then the NHRP process on the spoke is going to automatically keep track of the NHSs that are up, and they're going to automatically use the NHS that's actually up. So if one goes down, it'll figure that out, and then it'll automatically redirect all of the traffic that was designated for that next hop server to the other one. So that's hub redundancy single cloud. This is considered the less flexible of the two options. So yes, it's certainly easier to configure because you're keeping it in the same cloud. The problem here, though, is that from a routing perspective, you're going to be fairly limited, depending on, again, what protocol you're using, the intricacies of the specific protocols there. So dual hub SC is an option. It's just that you're messing around with a lot of the NHRP flags there. The other option is dual cloud. And with dual cloud, so this is dual hub, dual cloud, it's a lot more straightforward from a configuration perspective. What we've got is two hubs, and instead of just one DMVPN cloud, we've got two DMVPN clouds, each served by one of the hubs. And then we've got the spokes here. So how this would look on the spokes is that we would have two tunnel interfaces. We would have one tunnel interface going to the first hub and then another going to the second hub. Same thing on all other spokes. So we would have two tunnel interfaces right here. And then the advantage of doing dual cloud is that you can use routing to influence what you're going over, right? Mm-hmm. So with dual hub single cloud, because you're going out of a single interface, unless you're using something like BGP, it can be difficult to influence which cloud you want to go out of if you want to do route manipulation there, because your metrics are on a single interface. Like eIGRP, for example, you can't change the cost on the interface or the metric on the interface and affect one neighbor but not the other, and affect one hub but not the other, right? If you're changing the metric on the interface, you're changing the bandwidth or the delay, or you're using an offset list, you could potentially figure out some ways there. But at the end of the day, if you're changing a characteristic of the interface, you're affecting both hubs. That's the disadvantage of single cloud, right? With dual cloud, on the other hand, because you've got two separate tunnel interfaces, you can manipulate their routing independently, and now you've got more control over not just redundancy, but load sharing, right? You can say, I want to prefer this tunnel, or I want to prefer this tunnel, right? So it's not just redundancy. Now you've got more control over how the routing actually looks. It's more deterministic in that sense, instead of just straight load balancing between the two hubs. But the disadvantage here is obviously you're configuring a whole nother cloud. So it's a lot more drastic with change than just adding a couple map statements and another NHS statement to the single cloud. Now you've got a dual cloud environment where you're configuring two DMVPNs, and that's more configuration, more to take into consideration in terms of design, but dual cloud is generally regarded as the more robust solution. So that's one thing to keep in mind there. You've got two options, pick your poison, man. You're gonna have to think about your design considerations there and which one is gonna work for you. But they're both perfectly valid options. Both of them have their pros and cons. So that's that. Again, I'm not going to configure it because it's fairly straightforward. I mean, I did sort of configure the single cloud option, and the dual cloud is really obvious. You just configure a separate tunnel interface, give it a new subnet, replicate your NHRP config, but this time referring to hub 2, and you're off to the races. And then you can just use routing to, and now you've got two tunnel interfaces. Now you can, with, God forbid, OSPF, you could change the cost on one tunnel.
Yeah.
And not mess with the other, and then that way you could do your route manipulation there. The other thing to point out is that even if you're using single cloud, one of the nice things about OSPF in the DMVPN environment, and I struggle to say that, one of the nice things there is that if you're using point to multipoint, which again would only be an option if you're using phase 3, one of the nice parts there is that with point to multipoint, you can specify neighbor specific cost. So instead of being dependent on interface, you're dependent on the neighbor now. So we go into the OSPF process, configure a neighbor statement here. Let's say 1.1.1.1 was our hub, and then specify cost. This only works if it's point to multipoint. But it's one of the nice things about running OSPF over DMVPN. One of the only nice things about it. So that's that. The other thing I wanted to talk about was the FVRF, right? So front door VRF. This is a concept that isn't specific to DMVPN, but it's very useful in a DMVPN. So you'll notice earlier when I accidentally advertised the transport IP address over the tunnel there, you saw that there was that looped chain there. That's because they all share the routing table. So we haven't introduced any VRFs in this topology. So everything is in a single routing table. Both the underlay and the DMVPN routes share a routing table. So you can see these are all of our underlay routes, and we've got our tunnel routes all in one routing table. The way that an FVRF works, or a front door VRF, is you're basically putting your transport in a separate routing table by creating a VRF for it. So we can actually do that right now. It's a fairly unintrusive change there in the context of the whole fabric. Obviously, if you're defining a VRF, actually only NRD. I'm used to configuring these for MPLS. We just need an address segment. So, because this is VRF light here, what you would need to do is you would need to configure VRF-specific routing in the underlay there. So, if we were to do VRF forwarding transport, what would happen here is it would strip the IP address off, and then you would have to configure VRF-specific routing in the underlay, which you can do. So we can do that right now. So let's go to gig 1 real quick. I'm going to go no router OSPF 1 here. And that's going to bring that down. And then gig 1 VRF forwarding transport. we'll reapply the IP. And here we have to configure OSPF1 to operate in transport, and then we have to do capability VRF Lite to make it so it doesn't think it's a PE. And then we can go here and reapply this command to OSPF, and then in theory we should see our tunnels our neighbors come back up. And if I do show IP route, now we don't have the transport routes here. We've got the transport route in a separate VRF called transport, not transport. Transport here.
Nice.
And then what you'll see here is that OSPF adjacency change, this went down on the tunnel. That's because the tunnel is assuming that this destination, whatever it's resolving, is going to be in the global table, which it's no longer not. It's in transport or transport. So what we need to do on the tunnel side is do a tunnel VRF command and then tell it what the new underlay VRF is. So it's going to flap the tunnel line state, should come back up soon enough. So let's see. No, I shouldn't have boomer something. I did boomer something. My bad. The loopback here needs to be in the VRF as well. My bad. IP VRF forwarding transport, and then we'll go ahead and reestablish the IP address and give it a moment. Any day now. There we go. So the tunnel's back up. So the thing to remember is that when you're doing a tunnel, the tunnel source and tunnel destination have to be in the VRF that it's looking at. So by default, it's the global table. If you specify FVRF on the tunnel side, your tunnel source and tunnel destination have to be there as well. But as soon as you do that, show DMVPN, it's stuck in the NHRP state. So what I'm going to do is I'm going to go ahead and strip off the other commands here for the hub 2, just because we don't really need them right now. Because I'm not going to configure the other hub. And for some reason it's failing on the NHRP negotiation there. Debug NHRP, let's figure out why it's failing. NHS down. Let's see. Blah blah. Mission succeeded. Show the MVP. Okay. So if I had to take a guess, I would have to configure an FVRF on this side as well. Off the top of my head, I don't have a technical reason I need to do that, because this should just work. Attempting to send sending registration request. Yeah, then this should ping VRF transport 10.255.11 source 10.255.21. Oh well, if we don't know the route, then it's obviously going to fail.
There's your problem.
Yeah, let's figure out why that is real quick. Show IP route VRF transport. Got the route here. The loopback is here. Show IP route 10.255.255.21. That would certainly explain it. The question is why. Let's see. Did I boomer something here? Okay, well, not going to spend too much time. I'm an idiot. Because I put it in a separate VRF.
It removes the OSPF also?
It deactivated the
yeah.
on it. Yep.
There
so if I do show IP route, there we go. Yeah, that helps. So if I the tunnel came back up, so I'm not sure why it's still saying NHRP. But if I do a show DMVP, there we go, it's up. Yeah, okay. It's 8 p.m. That's my excuse.
It's getting late for you.
But the point is
almost
here,
bedtime.
Yes, but the point is here, we can configure our front door VRF, and that's going to separate our transport routes from our overlay routes. So our global table only has our transport routes, or not the overlay routes now, and then the transport VRF has our transport routes. So that's that. The last thing here, is going to be, so we covered two of the optimizations I wanted to look at, which was dual hub and the front door VRF. The other thing we're going to take a look at now is IPsec. So
sure.
That's going to be the total time I'll wrap this up with. So right now we've been doing DMVPN entirely unencrypted. So this traffic going over the internet, let's say the tunnel traffic is completely unencrypted, completely out in the open. If you've got some evil guy in the middle of the path with a packet sniffer, there goes all your data, right? So the way that we can rectify that is obviously with encryption. And before we do that, what I'm actually going to do is strip off all my work of configuring a front door VRF, and I'm about to just nuke it. Because having a front door VRF affects how you do your IPsec, and it's a couple of commands there that I can't be bothered to explain. So, oh, whoops, wrong thing. That's why there's a duplicate IP 21, and then IP OSPF 1 area 0, int loopback 0, IP address 10.255.21, and then I have to remember to put my OSPF command back on the loopback there. So let's make sure that I can actually ping the hub, which I can. So I'll shut the tunnel, make it, force it to redo the registration there. Okay, so that's that. So if I ping 172.16.22 or 0.22 source. So let's give that a try. Yep. Okay. So I can ping smoke to smoke. So my DMVPN is back up the way it is now without the transport VRF. It's funny. Doing the VRF took a while. Nuking it took 5 seconds. So the last thing here is going to be IPsec. So the IPsec workflow. This is not an IPsec video. Just to put that out there.
Yeah,
so I'm going to be flying by some of the IPsec commands here. So I'm just going to do PSK here. So first of all, I have to do a keyring. So let's do an DMVPN keyring. Here is going to be all address 0000, and then we'll do a pre-shared key. With IKV2, you can do local and separate remote keys. So we'll do remote DMVPN. And then I'll configure an IKV2 proposal, DMVPN proposal, PRF SHA-512 encryption, AES GCM 256, and then we'll do a DH group of 20. And then we'll configure IKV2 policy, DMVPN policy. We'll reference our proposal. And that's it here. And then we'll do our profile, DMVPN IKV2. We're going to set our authentication method. If I had time to do the signatures and certificates, we would do this, but we'll just do pre-share. If you want to do certificate, I will leave that as an exercise to the viewer. We'll match identity, remote, really FQDN, because I'm going to do an FQDN for the identity, domain, more Cisco, and then we'll set identity local to be an FQDN of hub1.more.cisco. And then finally, we'll set our keyring, local, and then DMVPN keyring. That's what I named it, right? KR? Yep. Okay. Crypto IPsec transform set, DMVPN IPsec TS. We'll set our encryption 256, and then the ASP SHA-512 HMAC. Now, the reason I wanted to talk about IPsec in this context is because if you're familiar with IPsec, you'll know there's two modes it can operate in: tunnel and transport. The difference is that tunnel is going to add on a whole new IP header. It's kind of like how GRE operates. It's going to tunnel the traffic in ESP. And then there's transport, which is just going to encrypt the payload and not add another outer header. Now, typically when you're working with a VTI, which is what Cisco calls its IPsec tunnels there, you want to do tunnel because you're using IPsec directly as the encapsulation. But in this case, we're using GRE because we're doing DMVPN. So what happens is if you do tunnel, you're going to have the outer header that GRE adds, because GRE happens first and then the IPsec encryption. So you're going to have the GRE and then the outer header and then IPsec and then another outer header. But the two outer headers are pointing to the exact same IP addresses. So you've got duplicate headers, which is adding a lot of unnecessary overhead. So when you're doing DMVPN, when you're doing IPsec over GRE, really, you're going to want to set this to mode transport. And that's just going to make sure that it doesn't try to add a duplicate header onto the final packet there. And then from here, it's fairly box standard: DMVPN IPsec, set IPv2 profile, DMVPN IPsec, and then we'll set our IPv2 rather, and then we'll set the transform set. And then just for giggles, we'll set the port 54 secrecy. And then I'm going to apply the IPsec to the tunnel interface later, but what I'm going to do first is copy this, because a lot of this is going to be boilerplate, paste it into my handy-dandy text edit document, and change a few values. So this is going to be spoke 1. Is there anything else I need to change? Nope, that's all. So spoke 1, and then this is going to be spoke 2. So I'm really just making sure here, because I've been warned once by not being careful about changing the values properly here and not having the security associations come up correctly, so I'm just being extra cautious here. Cool. All right, so we'll just deal with the first 3 spokes here. Now, when all is said and done, I'm making sure I set the identities correctly. When all is said and done here, you can apply a profile under tunnel protection, IPsec profile, DMVP, and IPsec. So what I'm going to do first is shut down the tunnel, because if I don't, it's going to start complaining. Int ton 0, because it's going to try to negotiate the encryption, and if I don't have a configure on all these other guys, it's going to, well, complain. Cool. Okay, so I'll no-shut this at this point, and then no-shut all the spokes, and then I did fly by it, but hopefully I got the configurations done. This is normal, because it's trying to send the packet before it does the IPsec. So it's going to say, I know you've got IPsec enabled, but this isn't actually an IPsec packet. So show crypto IPv2 security association. There we go. We've got all these security associations negotiated. So the key here is going to be, do we have our phase 2 negotiation done? And it appears we do. So at this point now, you can see we've got our OSPF coming up. And just to prove that this is working, so let's go ahead and do a trace route to 10301, source 10101 numeric. Let's prove that we've got the A-plane reachability, and we do. Let's prove that we are spoke to spoke. We can. And let's ping 10301 source from 10101. And what I'm going to do is I'm going to capture on the link to spoke 1, and I'm going to show you the effect that this had. So we'll do count, or was it repeat, 50. So let's take a look here. So IPsec encrypted DMVPN. So if you've seen an IPsec encrypted capture before, this should be nothing new to you. Boo-hoo, it's ESP. So notably, we've got the outer header because the underlay still needs to know how to route the traffic. So we can't encrypt the outer header. But we can, and then we can use the outer header to see that this is sourced from spoke 3. It's going to spoke 1, so presumably this is the echo reply to our ping. But everything else is encrypted under the ESP payload here. So this is, if you wanted to encrypt your DMVPN traffic, this is how you do it. ESP, and then if you add some malicious man in the middle there trying to capture your packets, well, all they're getting is ESP. So that's that. Probably gonna call it wraps here, eh?
Yeah, sure.
There was one more thing I wanted to cover, which is DMVPN Phase 4 is what they call it, which is FlexVPN. FlexVPN can do hub and spoke, so it's not DMVPN per se. It's FlexVPN, which is Cisco's fancy name for their IPv2 workflow. So it would be an IPsec VTI. It's basically their name for the hub and spoke variety of FlexVPN. Is basically a dynamic VTI. And the advantage there is that instead of a point-to-multipoint tunnel, it is multiple point-to-point tunnels, but you don't have to configure each individually. You configure one, they call it a virtual template interface, and then the spokes will, when they negotiate the IPv2 Security Association, the hub is going to create dynamically a virtual access interface with its configuration derived from the virtual template. So in that sense, if you wanted to, you could have, because the spokes are going to negotiate IPv2 with each other, if you do direct spoke to spoke there, they can run routing adjacencies directly between each other. So with DMVPN, we couldn't, but with FlexVPN, that is technically a possibility. So FlexVPN is cool. Don't have time to cover it, but there are a lot of security-oriented guides to help you configure FlexVPN there. If you are interested in learning how this concept of DMVPN and IPsec and hub and spoke VPNs evolves as we move on there.
Yeah, cool. Sounds good.
Yep.
All right. Anything else? Any last points you wanted to cover? Or?
Yeah. Nah. Unless there's any last questions there, I think I'm good for what we have to configure there.
Yeah. All right. So let us know if you do have any other questions, but I will switch it back to our webcams for now. You can stop the screen share.
Yep.
There we go. Okay. So that was quite a good, what do you call it, deep dive into DMVPN. Yeah, almost 3 hours. Solid deep dive. So as I said before, if you're studying for the CCNA, you obviously don't have to know it in this much detail. You should know what it is, but definitely if you're aiming for CCNP, CCIE, this is something you got to know. So watch the stream, follow along, make your own topology, try to configure it, and it's definitely something you should know.
And if you get stuck, there's always Jeremy's Discord and a bunch of our Discords to help you there.
Yeah, of course. Yeah, so
and I'm present on a lot of them.
Yeah. So if you want to get in touch with Kelvin and ask him questions about DMVPN or whatever else you're having troubles with, look for any Cisco Discord. He's basically in all of them as a moderator. Of course, I recommend mine. Just go to jeremysitlab.com/Discord. And Yep. And where else can people reach you? Get in touch with you.
I have a Twitter that people have found. I don't use it besides reading up on the news and reading up on drama because it's really fun. So I don't actually actively participate on Twitter. I have a LinkedIn where I'm semi-active. But Discord is going to primarily be the way that people can reach out.
Yep. Okay.
Yeah.
And he also has a YouTube channel, which I linked in the description. Haven't been posting much recently, but maybe in the future.
Give me some time.
All right. Looking forward to the next video. Okay. So, Kelvin, thanks for your time. Thanks for showing us DMVPN. And have you on again sometime in the future.
Yep.
All right. And thanks to everyone for watching. See ya.